The universe contains 2 trillion galaxies, and yet the space between them is so vast, so mercilessly empty, that crossing it may be the single hardest thing the laws of physics allow. So why do we keep asking if it is possible? What does it say about us that we cannot stop asking? How long would it actually take to cross that void and reach another galaxy? If questions like these make you feel simultaneously tiny and infinite, make sure to give this video a like. Now let's get started. Our own Milky Way stretches roughly 100,000 light-years from edge to edge, 100,000 years of uninterrupted light travel just to cross our home. And our home is not even a particularly large galaxy. There are galaxies out there hundreds of thousands of light-years wide, galaxies so massive they make the Milky Way look like a quiet suburb. But none of that is the point. The point is what lies beyond. Our Milky Way is not alone in the cosmos. It belongs to a gravitationally bound neighborhood called the Local Group, a family of roughly 50 to 60 galaxies held together by their mutual gravity, spread across a region of space about 10 million light-years wide. Most of them are small dwarf galaxies, modest satellites orbiting the bigger players. But 2 of those galaxies dominate everything, ours. And Andromeda, catalogued as Messier 31, is the closest large spiral galaxy to us. It sits at a distance of 2.5 million light-years. That is our nearest galactic neighbor of any real significance. And on the grand cosmic scale, that is practically next door. But here is where things start to mess with your head in a beautiful way. The light reaching your eyes tonight when you step outside and look at Andromeda, and yes, on a clear dark night far from city lights, you can actually see it with nothing but your naked eyes, a faint, ghostly smudge in the autumn sky. That light did not just leave recently. It left its source 2.5 million years ago, before anatomically modern humans existed, before Homo sapiens had ever stood upright and looked up at the sky in wonder, when our ancient relatives, the Australopithecus, were roaming the African savanna. The photons now landing on your retina were already halfway across the cosmos on their way to you. That is not poetry, that is physics. And Andromeda is the close one. The Triangulum Galaxy, the 3rd large member of our local group, sits about 3 million light-years away. Step outside our local group entirely and distances explode. The Virgo cluster, the nearest major galaxy cluster, is roughly 65 million light-years from here. The Perseus cluster, one of the most massive structures we know of, is about 240 million light-years away. And these are still, in cosmological terms, our backyard. The observable universe itself spans approximately 93 billion light-years in diameter. Inside that enormous sphere, astronomers now estimate there are somewhere in the range of 2 trillion galaxies. 2 trillion. Most people hear that number and let it bounce off. Do not do that. Let it land. 2 trillion individual galaxies, each containing hundreds of billions of stars, many of those stars surrounded by planets. And we are asking how long it would take to reach just one of them, the nearest one. Now here is where the story takes a turn that most science videos never talk about, and this part matters enormously. The universe is not just big, it is growing. Right now, as you sit here watching this, every galaxy beyond our local group is moving away from us. Not because the galaxies themselves are flying outward through space like projectiles, but because space itself is expanding. The very fabric of the cosmos is stretching, and galaxies are embedded in that fabric, carried along like raisins in a rising loaf of bread. They are not moving through space. Space is moving, and they are going with it. And this is not slowing down. Far from it, something called dark energy, a force or a property of space itself, or something else entirely that we genuinely do not yet understand, is causing the expansion of the universe to accelerate. Dark energy makes up approximately 68% of everything in the universe. Think about that. The dominant ingredient in the cosmos is something we cannot see, cannot directly detect, and cannot explain with any complete theory. We named it dark energy because we had to call it something. But what it actually is remains one of the biggest open questions in all of science. What we do know is what it does. It pushes, it stretches, it relentlessly drives galaxies apart at an ever-increasing rate. And this creates a consequence so profound it deserves its own moment of silence. There are galaxies in the observable universe, galaxies we can see with our best telescopes, galaxies whose ancient light has reached us across billions of years that we can never, ever travel to, not because we lack the technology, not because the journey would take too long, but because the expansion of space between us and them is already moving faster than anything in physics can overcome. Those galaxies are receding from us at superluminal speeds, not because anything is actually moving faster than light through space, which relativity forbids, but because the space between us and them is expanding so rapidly that the effective recession speed exceeds what can ever be bridged. Scientists call the boundary of what we can theoretically reach our cosmic event horizon. Everything beyond it is lost to us forever, not just practically, cosmologically, permanently. There are entire galaxies, each with hundreds of billions of stars, potentially billions of worlds, that already belong to a part of the universe we will never access, no matter what we build, no matter how long we wait, no matter how clever our physics becomes. The universe has already drawn that line. That is not a depressing thought, by the way. That is the universe in all its honest, humbling grandeur. It does not bend to our ambitions. It does not care about our timelines. And there is something strangely freeing about that. But, and this is critical, within our local group, within the gravitationally bound cluster of galaxies that includes Andromeda and Triangulum and dozens of dwarf galaxies, the situation is different. These galaxies are not receding. They are actually, in some cases, approaching. Andromeda itself is on a slow collision course with the Milky Way, a merger expected to begin in roughly 4.5 billion years. So our nearest galactic neighbor is coming to us, not running away. Within this reachable cosmic neighborhood, traveling to another galaxy is at least theoretically on the table. The question, the real, hard, scientifically grounded question, is what it would actually require. And this is where physicists, when they sit down and do the honest math using real propulsion concepts and real physics, arrive at numbers that are simultaneously awe-inspiring and deeply sobering. Speaking of journeys across unthinkable distances, this question of how long the trip would take leads directly to another one. What would happen to the human beings making it? That is a rabbit hole I went down hard in another video on the card above. In this video, I explore how long a generation ship would survive in space. And what the science actually says about that scenario is both fascinating and genuinely unsettling in ways I did not expect. Check that one out after this. The link is in the description and pinned on the comments. But right now, we stay here. Because before we talk about how anything or anyone could make this journey, we need to understand what we are actually crossing, what intergalactic space is really like. And the answer is weirder and more extreme than almost anyone realizes. Intergalactic space is not like the space between stars within our galaxy. The interstellar medium, the material between stars inside the Milky Way, is sparse, yes, but it is there. Gas clouds, magnetic fields, charged particles, cosmic rays, the occasional wandering rogue planet. It has texture, it has structure. Intergalactic space has almost none of that. Out in the void between galaxies, the average density of matter drops to something in the range of 1 atom, sometimes far less, per cubic meter. Let that number sit next to this one. The air filling the room around you right now contains roughly 25 million billion molecules per cubic centimeter. The difference between that and 1 atom per cubic meter is not just large, it is categorically incomprehensible. Intergalactic space is one of the most perfect vacuums in the known universe. Crossing 2.5 million light-years of that, of almost absolute nothing, is the challenge sitting at the heart of this video. So where does current science actually stand? What do the latest findings from astrophysics tell us about what is realistically possible, and what timescales are we actually looking at? Here is something to sit with until we continue. Even under the most optimistic physical framework, that real science, not fiction, not fantasy, but actual peer-reviewed theoretical physics, currently allows, the journey to Andromeda would still take longer than modern humans have existed on this planet. But there is a loophole buried inside Einstein's equations, a genuine, mathematically valid feature of the universe that means the crew making that journey might experience something radically different from what you would expect. It involves time itself bending in ways that feel almost impossible, and it changes everything about how we think about interstellar and intergalactic travel. We are getting into all of it now, so let us talk about the loophole. Because when most people think about traveling to another galaxy, they hit the same mental wall almost immediately. The distances are too vast. The time required is too enormous. The whole idea collapses under its own weight before it even gets started. And that reaction is understandable. It is even correct in a certain framing, but it is not the complete picture. And the part of the picture that is missing is one of the most beautiful, most disorienting, most genuinely strange contributions that any human being has ever made to our understanding of reality. It came from Albert Einstein, and it lives inside his theory of special relativity. Here is the idea, and pay close attention because this is not metaphor, this is not approximation, this is how the universe actually behaves, confirmed by experiment, confirmed by the satellites running the GPS on your phone right now, confirmed by particle accelerators, where subatomic particles age more slowly than their stationary counterparts in ways that are measured directly and precisely. Time is not fixed. Time does not tick at the same rate for everyone, everywhere, always. The rate at which time passes for you, your personal experience of seconds turning into minutes, turning into hours, depends on how fast you are moving. The faster you move through space, the slower you move through time. These two quantities are linked. They are two sides of the same coin. Einstein called it time dilation, and it is not a theory in the casual, everyday sense of that word. It is a confirmed, tested, documented feature of physical reality. And at speeds approaching that of light, time dilation becomes extraordinary. Here is a concrete example grounded in real physics. If a spacecraft, and we will talk about what it would actually take to build and power such a thing, could somehow accelerate to 99% of the speed of light and hold that speed, time aboard that vessel would flow at roughly 1/7 the rate it flows for someone watching from Earth. For every 7 years that pass on Earth, only 1 year passes for the crew. At 99.9% of light speed, the ratio becomes even more dramatic. At 99.99% more so still, the closer you approach light speed, the more extreme the effect becomes, and the math does not cap out at any comfortable number, it keeps going. At sufficiently high fractions of light speed, the dilation factor becomes enormous. Theoretically, you could traverse distances of millions of light years while aging only decades aboard the ship. That is the loophole. From Earth's perspective, from the perspective of everyone watching, waiting, left behind, the journey still takes millions of years. Andromeda is still 2.5 million light years away. Light still takes 2.5 million years to cover that distance. Nothing changes for the universe at large, but for the people on board, time itself compresses. The journey could be experienced, in principle, in a human lifetime. This is not science fiction. This is what the equations say. This is what physicists mean when they say relativistic travel does not violate any known laws of physics, but, and this is a large, heavy, consequential but, the engineering required to get anywhere near that kind of velocity is so far beyond anything we have ever built that describing the gap as enormous feels inadequate. Let us actually look at the numbers, because that is where the humility lives. The most energetic thing humanity has ever deliberately accelerated to high speed, deliberately, in a controlled, directed way, is a proton inside the Large Hadron Collider at CERN, the particle physics laboratory straddling the border between Switzerland and France. The LHC accelerates protons to approximately 99.999991% of the speed of light. That is genuinely breathtaking. That tiny particle is moving at a speed so close to the ultimate cosmic speed limit that the difference is almost philosophical. But a proton has a mass of approximately 1.67 times 10 to the negative 27 kilograms. It is, quite literally, one of the smallest things that exists. Now consider a spacecraft capable of carrying human beings across intergalactic space. Even a stripped-down minimalist vessel with a small crew and the absolute bare minimum of life support, food production, radiation shielding, and structural integrity would mass thousands of tons at minimum. More realistically, for a journey of millions of light years, you are talking about something vastly larger and heavier. The energy required to accelerate a meaningful mass to a meaningful fraction of light speed scales in a way that becomes almost theological in its extremity. The kinetic energy of an object increases as you push it faster, but not linearly. As you approach light speed, the energy required does not just grow, it diverges, it approaches infinity. You can never actually reach the speed of light with a massive object, no matter how much energy you pour in, because the closer you get, the more energy you need, and the more energy you add, the more mass energy the system contains, which makes it harder to accelerate further. It is a trap built into the geometry of space-time itself. So what does that mean practically? Let us look at what theoretical physicists have actually calculated, a concept that gets serious attention in the physics and aerospace engineering communities is constant acceleration travel. The idea is this: instead of trying to reach a top speed and cruise, a ship accelerates continuously at a rate equal to one standard gravity, that is approximately 9.8 meters per second squared, for the first half of the journey, then flips and decelerates at the same rate for the second half. This approach is appealing for two reasons. One, it would provide a comfortable, Earth-like gravitational experience for the crew throughout the journey. Two, it turns out to be remarkably efficient at generating relativistic speeds over time under constant one-gravity acceleration. After just 1 year of ship time, you are already moving at a meaningful fraction of light speed. After about 1 year of subjective time, you reach roughly 77% of light speed. Keep going, and the time dilation starts compounding dramatically. Now here is where the numbers become almost surreal. Physicist and author Paul Anderson, and later, in more rigorous form, by various physicists including those working on theoretical interstellar propulsion, worked out the subjective travel times for various destinations under constant one-gravity acceleration. The results are staggering. To reach the Andromeda Galaxy, 2.5 million light-years away, under constant one-gravity acceleration and deceleration, the crew would experience approximately 28 years of subjective time. 28 years. A person in their 30s could, in principle, leave Earth, travel to another galaxy, and arrive while still in their 60s. Meanwhile, back on Earth, back in the Milky Way, 2.5 million years would have passed. Everyone the crew had ever known would be gone. Not just dead, gone. Their bones, their cities, their languages, the entire civilization they left behind, every institution, every monument, every story dissolved into the geological and biological record of a planet that had continued spinning for 2.5 million years without them. Homo sapiens as a species is only about 300,000 years old. In the time those crew members spent traveling, our species could have risen and fallen more than 8 times over. That is the human cost hiding inside the physics, and that is assuming things go perfectly. In reality, constant one-gravity acceleration to relativistic speeds faces engineering obstacles that dwarf anything humanity has ever attempted. The fuel problem alone is staggering. Under any conventional propulsion concept, chemical rockets, ion drives, nuclear thermal, nuclear pulse, the fuel required to accelerate a ship to relativistic speeds is not just large, it is cosmologically absurd. The Tsiolkovsky rocket equation, which governs all rocket propulsion and which every aerospace engineer knows intimately, tells us that the fuel mass required grows exponentially with the velocity you want to reach. To get to even a modest fraction of light speed with a conventional rocket, you would need more fuel than exists in the observable solar system, by orders of magnitude. This is why serious theoretical physicists working on interstellar and intergalactic travel tend to focus on exotic propulsion concepts, ideas that sidestep or rewrite the conventional rules. Antimatter drives, laser sails, ramjets that scoop fuel from the interstellar medium, and then there are the ideas that live at the edge of known physics, concepts like the Alcubierre drive, which we will get into properly later in this script. But before we go there is something else worth understanding about the journey itself. Something that does not get discussed enough. Something that makes the physics even messier and the challenge even more profound. It is not just about speed. It is about what you are flying through. We touched on this briefly in part 1, the near-perfect vacuum of intergalactic space. But there is a threat lurking in that void that becomes catastrophically serious at relativistic velocities. Cosmic rays. Cosmic rays are charged particles, protons, atomic nuclei, electrons, accelerated to extreme energies by some of the most violent events in the universe, supernova explosions, neutron star collisions, the jets of active galactic nuclei, and other sources we are still working to fully understand. They travel through space at close to the speed of light, and they hit things, including living tissue. Inside the Milky Way, Earth's magnetic field and atmosphere protect us from most of them. Out in intergalactic space, there is no such protection. A crew traveling at relativistic speeds would face a cosmic ray environment that, depending on their velocity, could become lethally intense, not just over the course of the journey, but potentially quite quickly. The shielding mass required to protect human beings during a multi-decade relativistic voyage through intergalactic space is a serious, unsolved engineering problem. Some estimates suggest the shielding alone could outweigh the rest of the ship by factors of 10 or more, and then there is something even stranger. At very high fractions of light speed, the interstellar and intergalactic medium, remember 1 atom per cubic meter or less, starts to become a problem in a completely different way. From the perspective of a ship moving at 99.9% of light speed, those sparse, lonely hydrogen atoms are not drifting past gently. They are hitting the ship's hull with the effective energy of particle accelerator beams. Each individual impact is tiny, but at relativistic speeds, even the near void of intergalactic space becomes a radiation environment, serious enough to require active mitigation. There is no free lunch in the cosmos. Every advantage the physics offers, every beautiful trick of relativity, every compression of subjective travel time comes wrapped in engineering demands that are ferocious in their scale and complexity. The universe hands you the loophole with one hand and presents the bill with the other, and yet Here is what I find genuinely moving about all of this. Human beings are thinking about it anyway. Physicists are working on the equations. Engineers are exploring propulsion concepts. Astronomers are cataloguing the galaxies we might one day want to visit. The audacity of the project does not diminish the seriousness with which serious people are approaching it, because science does not ask whether something is convenient. It asks whether something is possible. And the honest answer to whether reaching another galaxy is physically possible, within the laws of nature as we currently understand them, is yes, barely, conditionally, with caveats the size of mountain ranges. But yes, that matters. That word, yes, matters enormously. There is a concept in physics that describes a region of space where the normal rules of travel simply do not apply, where a ship would not move through space at all, but instead carry a bubble of space around it, sidestepping the cosmic speed limit entirely without ever technically breaking it. It was proposed by a real physicist, published in a real journal, and the math checks out. The problem, and there is always a problem, is what it would take to build one. The answer involves a quantity of exotic matter so extreme that when you hear the number, your first instinct will be that I made it up. I did not. In 1994, a physicist named Miguel Alcubierre was sitting with Einstein's field equations, the mathematical framework that describes how mass and energy curve the fabric of space-time, and he asked a question that most of his colleagues would have considered either brilliant or completely unhinged, depending on their mood. What if, instead of moving a ship through space, you moved space itself around the ship? The idea sounds like wordplay at first, like a clever semantic trick that does not actually mean anything physical. But Alcubierre was not playing with words, he was playing with mathematics. And what he found when he worked through the equations was that a specific, geometrically precise configuration of space-time curvature could, in principle, create a bubble, a region of flat, undistorted space that contracts the space in front of it and expands the space behind it. A ship sitting inside that bubble would not be moving through space at all. The bubble itself would be moving, carrying the ship along like a surfer riding a wave. And here is the part that made the physics community sit up very straight. From the perspective of an outside observer, the bubble and the ship inside it could move at any speed, including speeds far exceeding that of light. Because the ship is not moving through space, it is not subject to the relativistic speed limit that applies to objects moving through space. The cosmic speed limit is a rule about motion through space-time. The Alcubierre drive, if it could be built, would be cheating at the game rather than playing faster. This is not fringe pseudoscience. Alcubierre published his paper in the journal Classical and Quantum Gravity, one of the most respected publications in theoretical physics. The mathematics is internally consistent. The solution is a genuine, valid solution to Einstein's field equations. There is always a but. And in this case, the but is one of the most formidable in all of theoretical physics. To create the space-time curvature that the Alcubierre drive requires, you need something that does not exist in any ordinary form anywhere in the known universe. You need exotic matter, specifically matter with negative energy density, not just low energy, not just cold, negative, a substance that, rather than curving space-time in the direction that normal mass and energy curve it, curves it in the opposite direction. A substance that, in a sense, has less than nothing. Now, here is where it gets genuinely complicated. Negative energy is not entirely fictional. There is a quantum mechanical phenomenon called the Casimir effect, named after Dutch physicist Hendrik Casimir, who predicted it in 1948, and which was experimentally confirmed in 1997, where two uncharged, perfectly conducting metal plates placed extremely close together in a vacuum experience a measurable attractive force. The reason involves quantum fluctuations of the vacuum itself, and one of the consequences is that the energy density of the vacuum between the plates is, in a technically meaningful sense, slightly negative compared to the energy density of free space. So negative energy is real, it exists. It has been measured, the problem is scale. The amount of exotic matter with negative energy density that early calculations suggested would be needed to build even a microscopic Alcubierre bubble was staggering, on the order of the mass-energy equivalent of an entire planet, converted into exotic negative energy matter. Some estimates went higher than that. The numbers were so extreme that most physicists filed the concept under mathematically interesting, physically hopeless, and moved on. But the story did not end there, because in 2012, a physicist working at NASA's Johnson Space Center named Harold "Sonny" White announced that he had found a way to dramatically reduce the exotic matter requirements by modifying the geometry of the warp bubble, shifting it from a simple sphere to a more complex, oscillating shape. White calculated that the required exotic matter could potentially be reduced by many orders of magnitude. His revised estimates, while still challenging, brought the numbers into a range that, while far beyond current engineering capability, no longer seemed categorically impossible for a sufficiently advanced civilization. White's work attracted enough institutional interest that NASA funded a small research effort, the Advanced Propulsion Physics Laboratory, informally known as EagleWorks, to explore these ideas experimentally. The results have been suggestive but not conclusive. No warp drive has been built. No exotic matter has been created in useful quantities. The field remains deeply theoretical, and then in 2021, a team of researchers, including physicist Eric Lentz, published a new analysis suggesting a different approach to warp geometry, one that might, under specific conditions, work without requiring negative energy at all. Using soliton solutions, a type of self-reinforcing wave pattern, Lentz proposed a warp bubble configuration that operates entirely within the known energy budget of conventional matter and energy. The paper generated significant discussion in the theoretical physics community, with reactions ranging from cautious optimism to pointed skepticism. The debate is ongoing. This is what real science looks like. Not a clean march from question to answer, but a long, messy, contested conversation where brilliant people disagree and the truth emerges slowly, fought for from every angle. So the Alcubierre drive and its descendants represent one branch of the theoretical propulsion tree, the branch that tries to sidestep the speed limit entirely by manipulating the geometry of space-time. There is another branch, quieter, less dramatic, but in some ways more grounded in physics we actually understand, and it involves one of the most powerful energy sources the universe has ever produced: antimatter. Every particle of ordinary matter has an antimatter counterpart, identical in mass, opposite in charge, and certain other quantum properties. When a particle and its antiparticle meet, they annihilate each other completely, converting their entire combined mass into pure energy with 100% efficiency. This is not approximate. This is not a useful simplification. 100% of the mass energy of both particles becomes radiation. For comparison, the most efficient nuclear fission reactions, the kind that power nuclear plants and atomic weapons, convert less than 1% of their fuel mass into energy. Fusion reactions, which power the sun and which we are still working to master here on Earth, do a little better, around 0.7% for hydrogen to helium fusion. Antimatter annihilation is not better by a little. It is better by a factor of more than 100 compared to fusion, and more than 10,000 compared to chemical combustion. An antimatter-matter rocket engine, operating by directing the gamma rays and charged pions produced by annihilation out of a magnetic nozzle, would be, by a very large margin, the most energetically efficient propulsion system physically possible. Physicists Robert Forward and Bryce Casenti both worked on detailed designs for antimatter propulsion systems in the 1980s and 90s, and their analyses suggested that a ship powered this way could realistically reach a significant fraction of light speed, given enough fuel. The catch, and you knew there was one, is that antimatter is extraordinarily difficult to produce and even more difficult to store. Here on Earth, the primary facility for antimatter production is again CERN. Their antiproton decelerator can produce antimatter in quantities that are, by any engineering standard, vanishingly small. We are talking about nanograms per year. A serious interstellar mission would require something in the range of hundreds of tons of antimatter at minimum. Current production rates would need to scale up by something like 20 orders of magnitude, that is 10 followed by 20 zeros, to even begin approaching mission-relevant quantities. Storing antimatter is its own separate nightmare. Antiparticles annihilate on contact with normal matter, including the walls of any container you might build to hold them. They must be kept in electromagnetic traps, suspended in vacuum, perpetually maintained. A power failure does not just interrupt the mission, it ends it catastrophically. So antimatter propulsion is real physics. The energy source is real. The engineering challenges are, for now, completely prohibitive. There is a third concept worth understanding, one that has the advantage of requiring no propellant aboard the ship at all. It was proposed in 1960 by physicist Robert Bussard, and it is called the Bussard Ramjet. The idea is elegant in its ambition. Instead of carrying fuel, the ship scoops up the hydrogen that naturally exists in interstellar space, that sparse but non-zero interstellar medium, and uses it as fuel for an onboard fusion reactor. As the ship moves faster, it collects more hydrogen per unit of time, which gives it more fuel, which accelerates it further in a theoretically self-sustaining cycle. When Bussard first proposed it, the concept generated enormous excitement. Carl Sagan discussed it enthusiastically. Science fiction writers adopted it wholesale. It seemed to solve the fuel problem elegantly. Then physicists looked at the details more carefully. The density of hydrogen in the interstellar medium is far lower than early optimistic estimates assumed. In intergalactic space, remember, it drops to barely 1 atom per cubic meter. The scoop required to collect enough hydrogen to sustain fusion at useful rates would need to be genuinely enormous. Some estimates suggest hundreds of kilometers in diameter, maintained against the ram pressure of interstellar gas hitting it at relativistic speeds. The magnetic fields needed to channel the hydrogen would themselves consume enormous energy, and proton-proton fusion, the specific reaction needed since interstellar hydrogen is just protons, turns out to be extraordinarily difficult to sustain under the conditions a ramjet would create. Subsequent analyses by physicists including T.A. Heppenheimer suggested that in many realistic scenarios, the drag created by the scoop exceeds the thrust produced by the fusion, meaning the ramjet actually slows down rather than accelerating. Later refinements have explored hybrid designs and alternative fuel cycles, but the original vision of the self-fueling ramjet climbing smoothly to relativistic speed has been substantially complicated by the physics. And yet, and this is the recurring theme of this entire conversation, the concept is not dead. Variations on the ramjet idea continue to appear in theoretical propulsion literature. Modified designs using laser-excited interstellar hydrogen or hybrid approaches combining onboard antimatter with ramjet fuel collection are being explored. The universe of possible solutions has not been exhausted, not even close. There is one more propulsion concept that deserves mention here, because it is arguably the most immediately practical of everything we have discussed, and also one of the most poetic, laser sails. The idea is simple and grounded entirely in conventional physics. Light carries momentum. When photons from a powerful light source strike a highly reflective surface, they impart a tiny push. In space, where there is no atmospheric drag or friction, even a tiny push applied continuously over a long enough time can build to remarkable speeds. The Breakthrough Starshot Initiative, a real, funded scientific project backed by some of the most prominent names in science and technology, has been exploring the feasibility of using an array of powerful ground-based lasers to accelerate a tiny, lightweight probe to roughly 20% of light speed. The target is Alpha Centauri, our nearest stellar neighbor at 4.2 light-years away. At 20% of light speed, the journey would take about 20 years. The key constraint is mass. To reach high speeds with a laser sail, the payload needs to be extraordinarily light, grams, not tons. Breakthrough Starshot envisions something like a postage stamp-sized chip carrying miniaturized sensors and a transmitter. Not a human crew, not a ship with life support, a wafer of electronics. Scaling that concept up to carry human beings, the mass jumps by many orders of magnitude, requires either a proportionally larger laser array or a proportionally lower final velocity, or both. The engineering scales badly, but as a proof of concept, as a demonstration that the fundamental physics works, laser sails represent something genuinely exciting. They are the most technically near-term pathway to sending any human-made object to another star system. Getting to another galaxy is a different order of challenge entirely. But every revolution begins with a step, and understanding the physics of what acceleration actually requires, what the universe will and will not allow, is how that first step gets made with honesty rather than fantasy. What all of these propulsion concepts have in common is that they are wrestling with the same fundamental adversary, the sheer quantity of energy required to cross cosmological distances at any speed that makes the journey meaningful. And when you ask where that energy might ultimately come from, when you push the question all the way to the end of its natural arc, you arrive at a place that forces you to think about the universe not as a backdrop to human activity, but as a resource, as a system with rules that can be understood and, with sufficient knowledge, potentially used. And that raises a question that has been lurking beneath the surface of this entire conversation, waiting for the right moment to surface. What kind of civilization would actually be capable of attempting this journey? Not in terms of culture or values or motivation, but in terms of raw physics. What level of energy production, what mastery of matter and space-time would a civilization need to possess before a voyage to another galaxy becomes something other than an impossible dream? The answer to that question involves a framework developed by a Soviet astronomer in 1964 that is still used by scientists today, and it scales the ambition of the project in a way that is, honestly, both humbling and electrifying. Here is the thing about that Soviet framework. The Kardashev scale, as it is known, it was not designed as science fiction world building. It was a serious attempt by a serious scientist to categorize what technologically advanced civilizations would actually look like based on physics. And when you place humanity on that scale, honestly, right now, today, with everything we have built and everything we know, the result is a number so small it is almost embarrassing. But the trajectory matters, and where that trajectory points, if it continues, is somewhere extraordinary. If you are enjoying this journey, make sure to give this video a like and subscribe. You will be part of a community that explores the cosmos together. In 1964, a Soviet astronomer named Nikolai Kardashev was doing something that, on the surface, sounds almost absurdly speculative. He was trying to figure out how to recognize an alien civilization, if we ever detected one, not by what it looked like, or what language it spoke, or what it believed, but by how much energy it used. His reasoning was straightforward and, once you hear it, almost obvious. Energy is the universal currency of civilization. Everything a civilization does, building, communicating, computing, traveling, surviving, requires energy. The more sophisticated the civilization, the more energy it commands. And energy, unlike language or culture or biology, leaves signatures in the physical universe that are detectable across vast distances. So Kardashev proposed a classification system, 3 categories, 3 tiers of civilizational power, defined not by technology or intelligence or social organization, but purely by energy consumption. He called it a scale of technological development, and it has carried his name ever since. A Type 1 civilization, a planetary civilization, fully harnesses all of the energy available on its home planet, every joule of sunlight striking the surface, every wind current, every ocean wave, every volcanic eruption. The total energy budget of a Type 1 civilization is approximately 10 to the power of 16 watts, 10 million billion watts, continuously available and fully under control. Where does humanity sit right now, today, on that scale? We currently consume energy at a global rate of approximately 2 times 10 to the power of 13 watts. That sounds enormous in absolute terms, and compared to any individual human or any country or any previous era of human history it is. But as a fraction of what a Type 1 civilization commands, it is roughly 1%. We are at approximately 0.73 on the Kardashev scale. Not Type 1, not even close to Type 1, 0.73. We are a pre-planetary civilization. We have not yet achieved full mastery of our own world's energy resources. We are, in cosmic terms, just getting started. A Type 2 civilization takes the next step, a step so enormous it makes the jump from a campfire to a nuclear reactor look trivial. A Type 2 civilization harnesses the entire energy output of its host star. Every photon, every watt of stellar radiation collected and directed and used. The total energy budget of a Type 2 civilization is approximately 10 to the power of 26 watts. That is 10 billion times more energy than a Type 1 civilization commands. The physicist Freeman Dyson, one of the most imaginative and rigorous scientific minds of the 20th century, proposed a specific structure that a Type 2 civilization might build to achieve this. A shell, or more realistically, a swarm of collecting structures, completely surrounding a star at a comfortable orbital distance, capturing its full energy output. This concept is now called a Dyson sphere, or more accurately a Dyson swarm, and it is an entirely legitimate theoretical engineering concept. Not magic, not fantasy. Physics, applied at a scale we cannot currently imagine but cannot rule out. Interestingly, astronomers have actually looked for Dyson spheres. A star with a complete energy-collecting shell around it would appear dim or invisible in visible light, but would glow brightly in infrared, because the waste heat from all that energy collection has to go somewhere. Several candidate stars have been identified over the decades that show anomalous infrared signatures and unexpected dimming patterns, the most famous being KIC 8462-8452, nicknamed Boyajian's star, or the WTF star, which shows irregular, dramatic dips in brightness that no conventional astrophysical explanation fully accounts for. The scientific consensus currently favors natural explanations, clouds of cometary debris, or possibly unusual stellar activity. But the honest answer is that we do not know for certain, and that uncertainty is, in itself, scientifically interesting. A Type 3 civilization controls the energy output of an entire galaxy. Every star, every stellar remnant, every black hole's accretion disk, the combined energy of hundreds of billions of suns, harnessed and directed by a single civilization. The numbers at this level become almost theological, somewhere around 10 to the power of 37 watts. A civilization at this level would be so far beyond our current capabilities that we might not even recognize their technology as technology. Their engineering projects might look, to our eyes, like natural astrophysical phenomena. Their communications might be indistinguishable from cosmic background noise. Their travel would operate on timescales and at velocities that we are only beginning to theoretically explore. And here is the quiet, profound implication sitting inside all of this. A journey to another galaxy. A voyage across 2.5 million light-years to Andromeda, or further still to the galaxies of the Virgo cluster, is not a Type 1 project. It is not even a Type 2 project. In terms of the energy requirements for propulsion at the speeds and scales we have been discussing, it begins to approach Type 3 territory. It is a galactic civilization undertaking. That is not a reason to dismiss the idea. It is a reason to understand it clearly, to see the project for what it actually is, not a logical extension of current aerospace engineering, but a fundamentally different category of endeavor, one that requires not just better rockets or better fuel, but a transformation of civilization itself so complete that the civilization arriving at another galaxy might be as different from us as we are from the microorganisms that first appeared in Earth's ancient oceans. But here is where the thinking gets genuinely interesting, because the Kardashev scale, useful as it is, has been critiqued and extended in ways that reveal something important about the nature of progress itself. Carl Sagan, whose ability to find the human meaning inside the coldest scientific facts remains, decades after his death, almost unmatched, proposed an extension of the Kardashev scale that added a new dimension, not just energy, but information. The total amount of information a civilization has processed, stored, and mastered. Sagan suggested plotting civilizations on a grid with two axes, energy on one side, information on the other, and he noted that humanity, despite being embarrassingly low on the energy axis, is not quite so low on the information axis. We have generated and preserved an enormous amount of knowledge, science, art, history, mathematics, philosophy, literature, accumulate over thousands of years and now stored in forms that could, in principle, persist for millions more. That matters because information, knowledge, is ultimately what drives the transitions between Kardashev levels. A civilization does not jump from Type 1 to Type 2 through brute force. It gets there through understanding, through figuring out the physics, the engineering, the materials science, the mathematics of stellar-scale energy collection. The knowledge comes first, the capability follows, which means that every physicist working on propulsion theory, every astronomer cataloguing the galaxies we might one day reach, every cosmologist untangling the mysteries of dark energy and the expansion of the universe, they are all, in a very real sense, contributors to a project that will not be completed in their lifetimes, or their children's lifetimes, or their children's children's lifetimes. But that makes the project no less real and no less worth contributing to. This is the long game that humanity has been playing since the first human being looked up at the night sky and felt the itch of a question forming. Now let us bring this back to the concrete, because there is a specific aspect of the intergalactic travel problem that most discussions skip over, and it fundamentally changes the calculation in a way that is both scientifically fascinating and deeply relevant to everything we have been exploring. It is the question of what happens to the destination while you are traveling to it. We established in Part 1 that the universe is expanding. Galaxies beyond our local group are receding from us, carried apart by the stretching of space-time. We also established that Andromeda is an exception. It is bound to us gravitationally within our local group and is actually approaching us rather than receding. So Andromeda, in principle, stays reachable. It is not being carried away by cosmic expansion. But what about galaxies beyond the local group? What about the Virgo cluster, 65 million light-years away? Or the galaxies at the edge of what we can currently observe? Here is the sobering reality. For any galaxy currently beyond our local group, the expansion of space is steadily increasing the energy required to reach it. Every year we wait, the destination is slightly further away, not because the galaxy is moving through space in any conventional sense, but because the space between us and it has grown, and because the expansion is accelerating. This is not a linear drift, it is a compounding one. There is a threshold, a specific distance from us, beyond which, even traveling at the speed of light in a straight line starting right now, you could never reach the destination because it is receding faster than you can close the gap. As we touched on in part 1, this boundary is called the cosmic event horizon. Everything beyond it is in principle permanently unreachable regardless of the technology employed. Current estimates place our cosmic event horizon at roughly 16 billion light-years away. The observable universe, remember, is about 46 billion light-years in radius, meaning a significant portion of what we can see is already beyond what we can ever reach. We can observe galaxies that are forever outside our causal grasp. We can study their light, map their structure, analyze their chemistry, but we can never send anything to them, and nothing from them can ever reach us again. They are already, in a meaningful physical sense, a different universe, the same space-time, but forever causally disconnected. This gives the question of reaching another galaxy an urgency that is not usually acknowledged. If there is a window, a cosmological window defined by the expansion rate and the geometry of our local universe, during which intergalactic travel to certain destinations remains theoretically possible, that window is not infinite. It is closing, slowly by human standards, but inexorably by any standard. The galaxies reachable from our local group under the most optimistic physical scenarios represent a finite and shrinking set. And while that set still contains millions of galaxies, more than enough to keep even the most ambitious civilization busy for geological ages, the fundamental point stands. The universe is not static. The opportunity space for cosmic exploration is not fixed. It is contracting around us, one Hubble time at a stretch, as dark energy does its slow, relentless work. There is something almost philosophical in that. The universe gave itself, gave life, gave intelligence, gave curiosity, a window to explore. And that window, like all windows, will eventually close. But we are here now. The window is open. And what we do with this moment, what we learn, what we build, what questions we refuse to stop asking, matters in ways that extend far beyond any individual human lifetime. Now, with all of that context established, the distances, the propulsion physics, the energy scales, the expanding universe and its shrinking horizons, it is time to ask the question that the whole conversation has been building toward, not just how long would it take in the abstract, but, given a specific propulsion system at a specific velocity, what are the actual numbers? What does the math say for each realistic scenario? What is the journey time to Andromeda under constant acceleration? What about under laser sail at 20% of light speed? What about under a theoretical antimatter drive at 99% of light speed? And what do those numbers mean for the human beings, or whatever beings we may one day become, who attempt the crossing? We are going to run through several scenarios, different propulsion systems, different velocities, different destinations, and for each one we are going to look at two numbers that matter above all others: the time experienced by the crew, their subjective, biological, lived experience of the journey, and the time elapsed back home in the Milky Way for everyone and everything left behind. These two numbers are not the same, and the gap between them is the most human part of this entire conversation. Let us start with the scenario we introduced a while ago. Constant acceleration at one standard gravity, 9.8 meters per second squared, maintained for the first half of the journey, then flipped and decelerated at the same rate for the second half. Destination Andromeda. Distance 2.5 million light-years. The relativistic equations for constant proper acceleration as experienced by the crew, not as measured from an outside frame, give us the following results. Total ship time for the journey, approximately 28 years. A crew member who boards the ship at age 30 arrives at Andromeda at around age 58. They experience nearly 3 decades of life, birthdays, conversations, meals, grief and joy and boredom and wonder, the ordinary texture of human existence, playing out across the void between galaxies, total time elapsed in the Milky Way, on Earth in the universe at large. Approximately 2.5 million years. The math on this is not mysterious or hidden. The Lorentz factor, the quantity that describes how much time dilation occurs at a given velocity, peaks at an extraordinarily high value during the middle portion of the journey when the ship is moving at its closest approach to light speed. During that central phase, the ship is covering light years of distance for every few days of crew time. The universe outside the hull is a blur of time and space, compressed beyond any intuitive human grasp. Now let us push further. What if, instead of one gravity of acceleration, a civilization had mastered propulsion capable of sustaining 10 gravities, 10 times Earth's surface gravity, continuously? The crew would need some form of acceleration dampening to survive. But let us follow the physics wherever it leads. At 10 gravities of constant acceleration and deceleration, the subjective travel time to Andromeda drops to approximately 21 years. The external time elapsed barely changes. It is still governed by the distance itself, still approximately 2.5 million years. The time dilation becomes so extreme at peak velocity that the ship is essentially translating vast cosmic distances in tiny slivers of subjective time. Now let us go in the opposite direction. What if we are not talking about relativistic travel at all? What if we are talking about something closer to what current physics might actually deliver within the next few centuries? Not a theoretical maximum, but a realistic near-future upper bound. Consider a ship traveling at 1% of light speed. This is still extraordinarily fast by any conventional measure, roughly 3,000 kilometers per second. It is many times faster than anything humanity has ever built, but it is not relativistic in any meaningful sense. At 1% of light speed, time dilation is negligible. A clock on the ship and a clock on Earth stay essentially synchronized. At 1% of light speed, the journey to Andromeda takes approximately 250 million years. Not for the crew, not for Earth, for everyone and everything equally. 250 million years ago, the dominant land vertebrates on Earth were early reptiles. The dinosaurs had not yet appeared. The continents were arranged in configurations that would be unrecognizable today. 250 million years is not a travel time, it is a geological epoch. At 1/10 of light speed, still faster than any spacecraft ever built, the journey stretches to 2.5 billion years. That is more than half the current age of Earth. More than half the time that life has existed on our planet. These numbers are not meant to be discouraging, they are meant to be honest. And their honesty serves a purpose. It shows exactly how critical the relativistic regime is. The difference between 1% of light speed and 99% of light speed is not a factor of 99 in travel time. Because of time dilation for the crew, it is a difference of millions of years versus decades. The physics rewards proximity to light speed not linearly but exponentially, in terms of what it delivers for the people making the journey. Now let us look at a destination beyond Andromeda. Let us aim at something further. The Virgo cluster, the nearest major galaxy cluster, containing over 1,300 galaxies, centered approximately 65 million light-years from here, under constant one-gravity acceleration and deceleration. The subjective travel time to the Virgo cluster is approximately 35 years. A crew member boards at 30 and arrives at 65, still within a human lifetime. Still, in terms of biological experience, manageable. The external elapsed time, 65 million years. The last time 65 million years passed on Earth, the Chicxulub impactor was just hitting the Yucatan Peninsula, and the non-avian dinosaurs were about to disappear forever. When the crew of this hypothetical ship arrived at the Virgo cluster, whatever species had evolved from our descendants, if any had, would be separated from us by the same gulf of time that separates us from the Cretaceous. Let us go further still, the Perseus cluster, 240 million light-years away, one of the most massive structures in the nearby universe, containing thousands of galaxies embedded in a vast cloud of superheated gas so enormous and so energetic that it produces the lowest note ever detected in the universe, a B-flat, 57 octaves below middle C, generated by the pressure waves of a supermassive black hole pumping energy into the surrounding gas. An actual cosmic sound, though at a frequency so impossibly low that a human ear would need to listen for 10 million years to hear a single cycle of it. Under constant one-gravity acceleration, the subjective travel time to the Perseus cluster, approximately 39 years. 39 years of crew time, an entire career from first day to retirement, spent crossing 240 million light-years, external time elapsed, 240 million years. And here is the calculation that I promised you, the one that stops people, because we have been talking about Andromeda, about the Virgo cluster, about the Perseus cluster, but let us aim at the far edge of what is theoretically reachable, the very boundary of our cosmic event horizon. Approximately 16 billion light-years away, the furthest point that a beam of light departing Earth today could ever theoretically reach, given the accelerating expansion of the universe. Under constant one-gravity acceleration and deceleration, the subjective travel time to the edge of our reachable universe, approximately 45 years, to cross 16 billion light-years of space, a distance so vast it contains trillions upon trillions of galaxies. The crew ages 45 years. They board in their 30s. They arrive in their late 70s. Old, perhaps, but alive, present, conscious, experiencing the arrival at the absolute frontier of what is cosmologically accessible from our corner of the universe, the external elapsed time for that journey, 16 billion years, longer than the current age of the universe itself. By the time such a ship arrived at its destination, the Milky Way would be unrecognizable, if it existed at all in any form resembling what it is today. The Sun would have exhausted its hydrogen fuel billions of years prior, expanded into a red giant, consumed the inner planets, and collapsed into a white dwarf, slowly cooling toward the absolute zero of a dying universe. And yet, and this is the part that takes your breath away if you let it, the crew would be 45 years older. Time dilation at those velocities, sustained across that distance, produces a compression factor so extreme that it borders on the incomprehensible. The universe outside the ship would be aging at a rate millions of times faster than the crew. The stars visible through the hull would be burning through their entire life cycles in what feels, to the travelers, like weeks. Galaxies would be evolving, merging, dying, on timescales that, from inside the ship, would be almost visible in real time if the crew could somehow perceive events at that accelerated rate. This is not fantasy. This is what the Lorentz transformation equations, written down by Hendrik Lorentz in the early 1900s and incorporated into Einstein's special relativity in 1905, actually predict when you apply them honestly and follow them without flinching. The universe has a loophole built into its deepest mathematical structure, and that loophole is time itself. But now let us sit with the other side of this coin. Because the mathematics is one thing, the human reality is another. And we would be doing this conversation a disservice if we treated the time dilation as purely a clever trick without acknowledging what it actually means for the people involved. Imagine you are one of those crew members. You board the ship, you say goodbye, and you know, in a way that is intellectually clear, even if emotionally impossible to fully absorb, that everyone you are saying goodbye to will be dead before you are 1 year into your journey. Not old, not distant, dead. And not just them, their children, their grandchildren, every human generation that follows them for the next millions or billions of years will live and die and be forgotten while you are still in transit. You are not just leaving Earth, you are leaving your era, your civilization, your entire chapter of cosmic history, the version of humanity that builds the ship, that waves goodbye at departure, is the last version of humanity you will ever know. Whatever exists when you arrive, if anything does, will have had millions of years to become something unrecognizable. This is a form of isolation so total, so absolute, that no human psychology has ever had to confront it. The loneliness of a long sea voyage, the displacement of emigrating to a new continent, the homesickness of the first astronaut spending months on a space station, these are real, genuine human experiences of separation. But they exist on a scale that is to intergalactic relativistic travel what a candle is to a supernova. The emotional and psychological architecture required to make such a journey as a human being does not currently exist. We have not built it. We may not be capable of building it in our current form, which raises a question that physicists and philosophers and futurists have been circling for decades. By the time humanity, or whatever we become, has the technological capacity to attempt an intergalactic voyage, will the beings making that journey still be human in any meaningful sense? The answer to that question depends on which of several trajectories you think the future holds. And there are several distinct possibilities, each grounded in real science, and each with its own implications for what the journey looks like and who, or what, makes it. The first possibility is biological augmentation, genetic engineering, synthetic biology, and our growing understanding of the mechanisms of aging suggest that it is at least theoretically possible to dramatically extend human lifespan. The science of aging, geroscience, as it is increasingly called, has identified several biological pathways that appear to govern how quickly organisms age, and researchers have already demonstrated the ability to extend healthy lifespan in model organisms by significant factors. If human lifespan could be extended to thousands of years, or if the aging process could be halted or reversed, then the multi-decade subjective journey time becomes far less daunting. A 1,000-year-old human in good health setting out on a 28-year voyage faces a very different psychological and biological reality than one of us doing the same thing today. The second possibility is suspended animation. The idea of putting crew members into a state of dramatically reduced metabolic activity, hibernation or something more extreme, has been explored in both science fiction and actual aerospace medicine research. NASA has funded studies into torpor-inducing technologies, and there are real biological phenomena, such as the way certain mammals dramatically reduce their metabolism during winter hibernation, that suggest the concept is not biologically implausible. If crew members could be kept in a state of deep metabolic suspension for the majority of the journey, waking only periodically or at arrival, the psychological burden of the transit becomes radically different. The question of what they wake up to remains, but the question of enduring the journey in conscious awareness largely disappears. The third possibility is the one that the most forward-thinking researchers consider most likely to be relevant on truly long timescales, the transition from biological to digital existence. If human consciousness, the patterns of neural activity, memory, personality, experience that constitute a person, can be sufficiently understood to be modeled, simulated, and ultimately transferred to a non-biological substrate, then the constraints of biological time and biological fragility become irrelevant to the journey. A digital mind does not age. It does not require food or oxygen or warmth. It does not suffer from radiation damage in the same way biological tissue does. It can, in principle, be copied, backed up, transmitted at the speed of light, and reconstructed at the destination. Whether this is possible, whether consciousness is the kind of thing that can be transferred to a different substrate while preserving the subjective experience of being that person, is one of the deepest unsolved questions in philosophy and neuroscience. We do not know. We do not have the tools yet to even know what kind of answer to look for. But the question is being asked seriously by serious people in serious institutions, and that matters because ultimately, the question of how long it would take to reach another galaxy is inseparable from the question of what kind of being makes the journey. The timescales, the challenges, the meaning of the experience, all of it depends on the nature of the traveler. Change the traveler, and you change the entire calculation. And this is perhaps the most honest and most beautiful thing that the physics of intergalactic travel reveals. It is not just a story about rockets and fuel and distance and time. It is a story about what we are and what we might become. It is a story about the relationship between intelligence and the cosmos, between the things that ask questions and the universe those questions are about. We are right now in the earliest possible chapter of that story, the chapter where the questions are first being asked with enough precision and enough scientific grounding to begin sketching real answers. The chapter where the gap between where we are and where we would need to be is measured not in decades of engineering, but in paradigm shifts of understanding. And yet here we are, asking the question anyway, running the calculations anyway, looking at the sky and refusing to accept that the lights out there are simply decorative. That refusal, that stubborn, irrational, gloriously human refusal to accept that something is too far away to be worth thinking about, is itself a form of navigation. It is how every journey, no matter how vast, actually begins. Right now, at this very moment, there are signals leaving Earth, radio waves, television broadcasts, military radar pulses, deliberate interstellar messages that have been traveling outward through space for decades. Some of them have already crossed distances measured in hundreds of light years. None of them will reach another galaxy in any timescale relevant to human civilization. But there is something else, something we sent deliberately with full knowledge of what we were doing and full awareness that we would never see the result. Something that encodes in physical form the fact that we existed, that we looked up, that we wondered, and that we tried to reach across the void. There is a small golden record drifting through space right now. It is attached to a spacecraft, one of two identical probes launched within weeks of each other in 1977, and it contains sounds and images selected to portray the diversity of life and culture on Earth. Greetings in 55 languages, music from every corner of the planet, Beethoven, Chuck Berry, a Navajo night chant, Georgian choral music, a Peruvian wedding song, the haunting sound of a Javanese gamelan, the sound of rain, wind, surf and thunder, a human heartbeat, the sound of a mother's first words to her newborn child. The record is made of gold-plated copper. Its cover is engraved with instructions for playing it, a kind of cosmic owner's manual written in the universal language of mathematics and physics for any intelligence that might one day find it and want to understand what kind of creature made it. That spacecraft is the Voyager probes. And while we are not dwelling on them specifically as a propulsion story today, we promised you something more interesting than that. They matter here for a different reason entirely. They matter because of what they represent. Because of the intention behind them, Carl Sagan, who chaired the committee that assembled the Golden Record, described the act of sending it as a message in a bottle cast into the cosmic ocean. And that metaphor is so precise, so emotionally accurate, that it has never been improved upon in the decades since. We sent a message, knowing we would never receive a reply, knowing the bottle would drift for millions of years before it came anywhere near another star system, knowing the chances of it ever being found were, by any rational accounting, vanishingly small. We sent it anyway, because the sending mattered, because the act of reaching out, even across impossible distance, even without expectation of response, is itself a statement about what kind of beings we are. That impulse to reach, to communicate, to say, we were here, we wondered, we tried, is the same impulse that drives the entire question at the center of this video. And it is not a weakness, it is not naivete, it is one of the most defining characteristics of intelligence as we know it. But let us talk about something even more remarkable than the Golden Record, something that connects the question of reaching other galaxies to a form of travel that has already happened, that is happening right now, continuously, in all directions simultaneously, and that we have been exploiting for decades without always appreciating the full depth of what we are doing. We are talking about light, not light as a speed limit, not light as a metaphor, light as an actual carrier of information across intergalactic distances, because every telescope we point at the sky is, in the most literal physical sense, a time machine. When the Hubble Space Telescope, or its successor, the James Webb Space Telescope, the most powerful infrared observatory ever built, launched in December of 2021 and now operating at the second Lagrange point, approximately 1.5 million kilometers from Earth, captures an image of a distant galaxy. It is not showing us what that galaxy looks like now. It is showing us what that galaxy looked like when the light we are receiving today first left it. For Andromeda, that means we are seeing it as it was 2.5 million years ago. For the galaxies of the Virgo cluster, 65 million years ago. For the most distant objects the James Webb Space Telescope has imaged, galaxies so far away they existed when the universe was only a few 100 million years old. We are looking back more than 13 billion years. More than 90% of the way back to the Big Bang itself, the James Webb Space Telescope has already transformed our understanding of early galaxy formation in ways that have surprised and, in some cases, genuinely unsettled the scientific community. Galaxies that our models predicted should not exist in the early universe, galaxies that are too massive, too structured, too chemically complex for their age, are showing up in Webb's images with uncomfortable frequency. As of the time of this script, astronomers are actively working to reconcile these observations with existing theoretical frameworks. Some researchers suggest the models need refinement. Others argue the observations reveal something more fundamentally unexpected about how galaxies form and grow. This is science working in real time, the universe surprising us, the data pushing back against the theory and forcing us to think harder, look deeper, question assumptions we did not even know we were making. And this is the sense in which the journey to other galaxies has already begun. Not physically, not with any ship or engine or propulsion system, but epistemically, in terms of knowledge, understanding, connection. We have already reached other galaxies with our eyes and our instruments. We have already decoded the light that traveled billions of light years to reach our detectors and extracted from it information about chemistry, temperature, motion, structure, history. We have mapped the distribution of galaxies across hundreds of millions of light years. We have detected the gravitational waves produced by black hole mergers in galaxies far beyond our own. We have identified the specific chemical signatures of elements forged in stars that burned out long before our sun was born. In a profound sense, we already know other galaxies. Not the way you know a place you have walked through, breathed in, touched with your hands, but the way you know something you have studied deeply and cared about intensely, the way a historian knows ancient Rome, or a marine biologist knows the deep ocean floor, intimately, rigorously, with genuine emotional investment. And that knowledge has revealed something about the nature of galaxies, including our own, that reframes the entire question of traveling between them. Galaxies are not isolated, they are not discrete, self-contained islands floating in empty space separated by pure nothingness. The universe is structured on scales far larger than individual galaxies, and that structure has a name, the cosmic web. The cosmic web is one of the most visually and conceptually stunning features of the universe at its largest scales. It is a vast three-dimensional network of filaments, threads of gas, dark matter, and galaxies stretching across hundreds of millions of light years, connecting galaxy clusters like nodes in an incomprehensibly large net. Between the filaments lie enormous voids, regions of space hundreds of millions of light years across that contain almost nothing, no galaxies, no significant gas clouds, just vast dark, nearly empty bubbles of space. When cosmologists simulate the large-scale structure of the universe, using supercomputers running physics calculations for weeks at a time, modeling the gravitational interaction of billions of simulated particles representing dark matter and ordinary matter from just after the Big Bang to the present day, the result looks almost biological, like a neural network, like the branching structure of neurons in a brain, or the mycelial network of a fungus spreading through soil. The largest structures in the universe bear an uncanny resemblance to the smallest structures of biological complexity. Whether that resemblance is meaningful, whether it reflects some deep mathematical principle about how networks form under certain physical constraints, or whether it is simply a coincidence of visual pattern, is an open question. But it is one of those questions that, once you encounter it, never quite leaves you. The cosmic web matters for our conversation because it reveals that the space between galaxies is not uniform. The intergalactic medium, that near-perfect void we discussed in Part 1, is not the same everywhere. Along the filaments of the cosmic web, the density of gas and dark matter is higher. The filaments are highways of a sort, not highways in any sense that makes travel easier, but highways in the sense that matter preferentially flows along them. Galaxies form preferentially along them. The large-scale movement of gas and matter in the universe follows the structure of the web. This has a practical implication for any civilization thinking seriously about intergalactic travel. The choice of route matters, not enormously, given the scale of the challenge. Crossing a filament versus crossing a void does not change the fundamental physics of propulsion or time dilation, but it changes what you encounter along the way. It changes the density of the medium your ship is moving through. It changes the radiation environment. It changes the availability of any resources you might want to collect or use en route. And it changes something else, something subtler, but perhaps more important. It changes what you learn by going. The filaments of the cosmic web are where the action is, where gas is cooling and condensing, where new stars are forming, where the dynamic processes of galaxy evolution are most active. A journey along a filament is a journey through the living structure of the universe. A journey through a void is a journey through silence so complete it makes interstellar space seem crowded. Both have their own kind of beauty. Both have their own scientific value. but they are profoundly different experiences of what it means to be in intergalactic space. Now let us talk about something that does not come up often enough in discussions of intergalactic travel, and that fundamentally shapes every calculation we have done so far: navigation. In space, navigation is already extraordinarily complex. Spacecraft navigating within the solar system, probes sent to Mars or Jupiter or the outer solar system, require constant tracking and course correction from teams of engineers on Earth, using radio signals and precise orbital mechanics to keep the vessel on its intended path. Small errors in trajectory, uncorrected, compound over time. A tiny deviation in direction, sustained across millions of kilometers, becomes a vast miss at the destination. Now scale that challenge to intergalactic distances. A ship traveling from the Milky Way to Andromeda, 2.5 million light-years, needs to arrive at a specific location within that galaxy, not just somewhere in the general direction of Andromeda, a specific star system, a specific planet, if the mission has that kind of precision ambition. At those distances, an angular error of even a tiny fraction of an arcsecond at departure translates to a positional error of thousands of light-years at the destination. Maintaining navigational accuracy across 2.5 million light-years over a journey time of 28 years of crew time requires a level of precision in both initial trajectory and ongoing correction that makes current deep space navigation look like pointing a garden hose. The reference points you use for navigation, pulsars, quasars, the positions of known stars, are themselves moving relative to you during the journey. The coordinate system of the universe does not stand still while you cross it. Pulsar timing, the use of millisecond pulsars as natural cosmic clocks, whose signals are so regular they can be used to establish position in three-dimensional space with extraordinary precision, has been seriously proposed as a navigation system for interstellar and intergalactic missions. Pulsars are distributed throughout the galaxy and beyond, and their signals are detectable across enormous distances. A ship equipped with sensitive enough receivers and the computational capacity to solve the timing equations could, in principle, determine its position and velocity to high precision at any point during the journey. The Galactic Positioning System, sometimes abbreviated as GPS in the cosmic sense, though the acronym has obvious terrestrial competition, is a real concept that aerospace engineers and physicists have explored in peer-reviewed literature. It is one of the quieter, less glamorous, but genuinely necessary components of any serious thinking about long-distance space travel. And then there is the question of communication. If a ship leaves the Milky Way for Andromeda, how does it stay in contact with home? Radio signals travel at the speed of light. A signal sent from a ship at the halfway point of the journey, 1.25 million light-years from Earth, takes 1.25 million years to arrive. The civilization that receives that signal is not the civilization that sent the ship. It is a civilization separated from the launch event by more than 1 million years of history. In any meaningful human sense, the ship is not in contact with home. It is on its own, completely, permanently. From the moment of departure, the crew is the entirety of their communicative world. Whatever they know when they leave is, in terms of real-time input from Earth, all they will ever know about the civilization that built their ship. Future updates, scientific discoveries, political changes, technological breakthroughs happening back home arrive, if at all, so delayed as to be historical records rather than news. This total communicative isolation is, alongside the temporal displacement of time dilation, one of the most psychologically extreme aspects of intergalactic travel, and it is one that current human psychology is completely unprepared for. Our social brains evolved over millions of years in small, tightly connected groups where the loss of social connection was a genuine survival threat. are not equipped to handle permanent, irrevocable severance from all of civilization. The clinical literature on extreme isolation from Antarctic expeditions, submarine deployments, and long-duration spaceflight already reveals how profoundly the human psyche struggles with even temporary, partial isolation. The full disconnection of an intergalactic voyage is categorically beyond anything that framework describes. Which brings us to a question that has been sitting quietly at the edge of this conversation for a while now. A question that the physics almost forces upon us once we take seriously both the extraordinary timescales involved and the extraordinary changes those timescales would bring to any civilization doing the preparing. The question is this: would a civilization advanced enough to actually build an intergalactic ship still want to use it? Not philosophically, not as a values question, physically, practically. By the time a civilization has achieved the energy mastery, the materials science, the propulsion technology, and the navigational precision required for intergalactic travel, what else might it have achieved? What other options might be available to it that make a physical journey across millions of light years, with all its costs and challenges, seem less compelling than alternatives we cannot currently imagine? This is the question that we are going to explore now, because the honest answer is that the most advanced civilizations may not travel between galaxies the way we are imagining. They may do something stranger, something more efficient, something that the physics already hints at if you look in the right places, and one of those hints involves a phenomenon so extreme, so geometrically bizarre, so mathematically rich that it has occupied the best minds in theoretical physics for more than a century and still refuses to be fully understood. There is a solution to Einstein's field equations. It's a legitimate, mathematically valid solution known since 1935. It describes a tunnel through spacetime itself, not a metaphor, not a narrative device, a geometric feature of the universe that connects two distant regions of space through a passage that could, in principle, be shorter than the space it bridges. Physicists call it an Einstein-Rosen bridge. You probably know it by another name. And what the latest research in theoretical physics says about whether it could ever be used, whether anything or anyone could ever pass through one, is far more nuanced, far more surprising, and far more connected to the deepest mysteries in all of science than most people realize. In 1915, Albert Einstein published his general theory of relativity, a complete reimagining of gravity, not as a force between masses, but as the curvature of space-time caused by the presence of mass and energy. The equations he arrived at were elegant, compact, and ferociously difficult to solve. They describe the universe not as a static stage on which events unfold, but as a dynamic, living geometry, bending, stretching, rippling in response to everything within it. Within months, a German physicist and astronomer named Karl Schwarzschild, working at the Russian front during the First World War, in conditions that would kill him within the year, found the first exact solution to Einstein's equations. He was solving for the geometry of space-time around a perfectly spherical, non-rotating mass. What he found was correct, complete, and contained something that nobody at the time fully understood. At a specific radius from the center of any sufficiently compressed mass, a radius now called the Schwarzschild radius, the equations produced a result that seemed, on its surface, like a mathematical pathology, a singularity, a point where the equations broke down, where physical quantities like space-time curvature became infinite, where the normal rules of physics as then understood simply stopped applying. Einstein himself thought the singularity was a mathematical artifact, a quirk of the idealized geometry rather than a prediction of something real. He was wrong. What Schwarzschild had found was the mathematical description of what we now call a black hole. It took decades for the physics community to fully accept what the equations were actually saying. But by the 1960s, the theoretical framework was solid and observational evidence began accumulating rapidly. Today we know that black holes are not mathematical curiosities. They are real. They are abundant. They are among the most consequential objects in the universe, but that is not where our story goes right now. Because in 1935, Einstein, working with his colleague Nathan Rosen, examined the Schwarzschild solution more carefully and found something inside it that was even stranger than the black hole itself. When you extend the Schwarzschild geometry maximally, when you map out every mathematically valid region of the spacetime it describes, you find that the geometry contains not one region of space, but two separate regions of spacetime, connected at the singularity. Two universes, or two distant regions of the same universe, joined at a point of infinite curvature through a bridge of curved spacetime. Einstein and Rosen called it a bridge. The physics community, following the terminology introduced later by physicist John Wheeler, one of the great scientific wordsmiths of the 20th century, the man who also gave us the terms black hole, quantum foam, and it from bit, eventually settled on a more evocative name, a wormhole, and the question that has haunted theoretical physics ever since is deceptively simple. Can you actually go through one? The answer, as it turns out, is not a clean yes or no. It is a layered, qualified, deeply illuminating conversation about the nature of space-time, quantum mechanics, and the limits of what physics currently knows. And working through that conversation honestly reveals something about the structure of the universe that is, in my view, one of the most profound things that science has ever uncovered. Let us start with the basic geometry. A wormhole, in the simplest theoretical description, is a tunnel connecting 2 points in space-time. Those points could be far apart in space, different regions of the same galaxy, or different galaxies entirely. They could, in principle, be far apart in time as well, though that introduces complications we will come back to. The tunnel provides a shortcut, a path between 2 points that is geometrically shorter than the path through the surrounding space. To understand why this matters for intergalactic travel, think about a simple analogy. Take a sheet of paper and mark 2 points on opposite ends. The straight line distance between them, measured along the surface of the paper, is the length of the sheet. Now fold the paper so that the 2 points are nearly touching. The distance through the paper, through the material itself, is now tiny. The distance along the surface has not changed, but there is now a much shorter path available if you can pass through the paper rather than along it. A wormhole does something conceptually similar with space-time. The distance between, say, the Milky Way and Andromeda, 2.5 million light-years measured through the intervening space, remains exactly what it is. But if a wormhole existed connecting a point in our galaxy to a point in Andromeda, the distance through the wormhole might be far smaller, potentially traversable in a human lifetime, potentially traversable in minutes, hours, or days, depending on the geometry of the specific wormhole. No propulsion required, no time dilation calculation, no fuel budget. You enter on one side and exit on the other. This sounds almost too good to be true, and predictably it is complicated. The original Einstein-Rosen bridge, the wormhole that emerges naturally from the Schwarzschild solution, is not traversable. It is not just difficult to pass through or dangerous. It is geometrically, mathematically, fundamentally impossible to traverse. Here is why the Einstein-Rosen bridge connects 2 regions of space-time, but the connection does not persist. The bridge forms and then pinches off, collapses, in a time so short that not even light can pass through before it closes. From the perspective of anyone trying to use it, the throat of the wormhole snaps shut before they can cross it. The geometry is dynamic in a way that makes transit impossible, not because of any engineering limitation, but because of the mathematics of the spacetime structure itself. This was understood by the physics community for decades, and it seemed to close the door on wormholes as anything other than mathematical curiosities. But in 1988, a physicist named Kip Thorne, who would go on decades later to share the Nobel Prize in Physics for his role in the detection of gravitational waves, and his colleagues Michael Morris and Ulvi Yurtseva published a paper that asked a different question. Instead of asking what wormholes the known solutions to Einstein's equations produce naturally, they asked, what would a traversable wormhole require? What properties would it need to have, geometrically, physically, in order to stay open long enough for something to pass through? The answer they arrived at was elegant and disturbing in equal measure. A traversable wormhole requires exotic matter, specifically matter with negative energy density, concentrated at the throat of the wormhole in sufficient quantities to hold it open against the tendency of gravity to collapse it shut. The same exotic matter we encountered when we were discussing the Alcubierre drive, the same Casimir effect hinting, quantum mechanically suggestive, currently unproducible in useful quantities substance that sits at the intersection of general relativity and quantum field theory. The requirement for exotic matter to stabilize a wormhole is not a design flaw or an engineering challenge in the ordinary sense. It is a deep statement about the relationship between geometry and energy, about what the universe permits and what it does not. And whether sufficient exotic matter can exist in nature or be produced by a sufficiently advanced civilization remains genuinely unknown. Here is where the story takes a turn that not many popular science discussions acknowledge. Because in the decades since the Morris-Thorne paper, the theoretical landscape around wormholes has shifted in ways that are both discouraging and, in some respects, unexpectedly illuminating. A series of theoretical results, sometimes grouped under the heading of topological censorship theorems, suggests that general relativity taken alone may be fundamentally hostile to traversable wormholes. The mathematics seems to enforce a kind of cosmic decency. Structures that would allow faster-than-light travel or closed time-like curves, loops through time, appear to be forbidden by the self-consistency of the theory. Whenever you try to construct one, something in the physics seems to conspire against you. Singularities form, energy conditions are violated in ways that destabilize the structure. The universe, it seems, does not want to be shortcut. But, and this is one of the most exciting developments in theoretical physics of recent decades, general relativity is not the whole story. It cannot be. General relativity is a classical theory describing the universe at large scales. Quantum mechanics describes the universe at small scales, and the two theories, despite each being extraordinarily successful in their respective domains, are fundamentally incompatible with each other. They cannot both be completely correct. The reconciliation of general relativity and quantum mechanics, the search for a theory of quantum gravity, is arguably the central unsolved problem of theoretical physics, and wormholes sit right at the intersection of that problem. In 2013, physicists Juan Maldacena and Leonard Susskind, two of the most influential theoretical physicists alive, published a paper whose title contained an equation that became instantly iconic in physics circles. ER equals EPR. Einstein-Rosen bridge equals Einstein-Podolsky-Rosen correlation. Let us unpack that slowly, because it is worth understanding. Einstein-Rosen bridges are wormholes. We have established that. Einstein-Podolsky-Rosen correlations refer to quantum entanglement, the phenomenon where two particles, once they have interacted, share a quantum state in such a way that a measurement on one instantly affects the other, regardless of the distance between them. Einstein himself famously called entanglement spooky action at a distance, and spent years trying to prove it was an artifact of incomplete theory rather than a real physical phenomenon. He was wrong again. Quantum entanglement is real, experimentally confirmed beyond any reasonable doubt, and now a foundational tool in quantum computing and quantum cryptography. What Maldacena and Susskind proposed was a deep, structural connection between these two seemingly unrelated phenomena. They suggested that the geometric connection of a wormhole and the quantum connection of entanglement might be, at a fundamental level, the same thing. That space-time connectivity, the fabric that allows 2 points in space to be geometrically related, is built from quantum entanglement. That the geometry of the universe emerges from quantum information. If this is correct, and it remains an active, contested, intensely researched area of theoretical physics, it has staggering implications. It suggests that the fabric of space-time itself is knitted together by quantum correlations. That geometry and information are not separate things, but two aspects of the same underlying reality. And it suggests that wormholes, rather than being exotic curiosities requiring impossible amounts of exotic matter to maintain, might be deeply connected to the most fundamental structure of physical reality. In 2022, a team of physicists including Maria Spyropoulou at Caltech used a quantum computer, Google's Sycamore processor, to simulate a simple quantum system exhibiting properties consistent with a traversable wormhole. The result was published in the journal Nature and generated enormous discussion and considerable debate within the physics community. Some physicists called it a landmark result. Others argued it was a simulation of a wormhole-like quantum system, not evidence of an actual wormhole, and that the distinction matters enormously. The debate itself is illuminating. It shows how alive, how contested, how genuinely unresolved the question of wormholes remains. This is not settled science. This is the frontier. And the frontier is messy and exciting and unfinished in ways that the textbooks never quite capture. What does all of this mean practically for the question of reaching another galaxy? In the near term, meaning the next few centuries or even millennia, almost certainly nothing. We do not know how to create wormholes. We do not know whether traversable wormholes can exist in nature. We do not have access to exotic matter in any meaningful quantity. The ER equals EPR connection, if it is real, is a profound insight about the nature of reality. But it does not hand us an engineering blueprint. In the longer term, across timescales that make civilizational humility genuinely necessary, the picture is more open. If quantum gravity is eventually understood, if the connection between geometry and entanglement is worked out fully, if exotic matter can be produced or harnessed, if the topological censorship theorems have loopholes that a sufficiently advanced understanding of physics can exploit, then wormholes move from mathematical curiosity to potential engineering target. That is a lot of ifs. But physics has a history of turning theoretical impossibilities into engineering realities. Heavier-than-air flight was considered physically marginal by serious scientists in the late 19th century. Nuclear energy was theoretical fantasy until it was not. The transistor that makes every computer on Earth possible was a quantum mechanical phenomenon, harnessed through understanding rather than intuition. The history of applied physics is a history of theoretical insights becoming practical tools within timescales that surprised the theorists who developed them. The universe does not promise us wormholes. It does not guarantee shortcuts, but it does not appear to flatly forbid them either, and in the cosmic game of what is possible, that ambiguity is everything. There is one more piece of this picture worth examining before we move on, because wormholes are not the only geometric feature of the universe that might in principle be relevant to long-distance travel. There is another class of objects, rotating black holes specifically, whose internal geometry, according to general relativity, contains features that have led some physicists to speculate about connections between distant regions of space-time, a rotating black hole described by the Kerr metric, derived by New Zealand mathematician Roy Kerr in 1963, has an internal structure far more complex than a simple Schwarzschild black hole. At its center, instead of a point singularity, the Kerr solution produces a ring singularity, a singularity shaped like a circle rather than a point. And the mathematics of the Kerr geometry contains, at least formally, the possibility of paths through the ring that connect to other regions of space-time. Whether these connections are physically real, whether they survive the introduction of actual matter and radiation into the black hole, whether they persist once quantum effects are taken into account, is deeply uncertain. The internal structure of rotating black holes is one of the most actively debated topics in theoretical physics. But the fact that the mathematics produces these features, even as formal solutions, tells us something. It tells us that the universe's geometric rulebook is richer and stranger than it appears from the outside. And that strangeness, that richness, is the universe's ongoing invitation to keep asking questions, because ultimately, every limitation we have discussed in this video is a limitation of current knowledge, not a limitation of nature itself. The universe is not withholding the answers. It is simply waiting for us to develop the understanding necessary to find them, which brings us, in Part 8, to a question that might seem like a step backward, but is actually a step deeper. Because we have been talking throughout this video as though the goal, reaching another galaxy, is self-evidently worthwhile, as though the motivation is obvious, as though any civilization capable of the journey would naturally want to make it. But why, exactly? What would compel beings, human or otherwise, to attempt one of the most extreme undertakings physically possible? What waits in another galaxy that does not exist in our own? Is there a scientific case for the journey that goes beyond curiosity? Is there a survival argument, a reason rooted not in wonder but in existential necessity? And perhaps most intriguingly, is there any evidence in the vast observational record that our telescopes have accumulated that someone else may have already made the attempt? That last question is the one that makes the answer uncomfortable in the best possible way. If you are still watching, you already see the universe differently than most people do. Don't forget to subscribe and hit the like button. Every video we go somewhere extraordinary together and bring back something that changes how you see everything. Here is the thing that keeps some astronomers quietly unsettled at night. The universe is approximately 13.8 billion years old. Our sun is about 4.6 billion years old. That means there was a window of more than 9 billion years during which other stars formed, other planets cooled, other chemistry assembled itself into complexity, and other intelligence potentially arose and developed before our solar system even existed. 9 billion years is long enough for a civilization to have crossed not just our galaxy but potentially our entire local group multiple times over, even at the modest speeds of conventional physics. So where is everybody? And what do the most anomalous signals our telescopes have ever detected actually tell us, if anything, about that question? In 1950, the physicist Enrico Fermi was having lunch with colleagues at Los Alamos National Laboratory, the research facility in New Mexico, where just a few years earlier, the first nuclear weapons had been designed and built. The conversation drifted, as conversations among physicists sometimes do, toward the question of extraterrestrial intelligence. Someone made a comment about the statistical likelihood of other civilizations existing in the galaxy. The numbers, even by conservative estimates, seem to favor abundance. The galaxy is old. It contains hundreds of billions of stars. A significant fraction of those stars have planets, A significant fraction of those planets sit in habitable zones where liquid water can exist. The math, loosely applied, suggests that life, and perhaps intelligence, should be common. Fermi listened, thought for a moment, and then asked a question so simple, so direct, so devastatingly precise that it has echoed through physics and astronomy ever since. Where is everybody? If intelligent civilizations are statistically likely to be common in a galaxy 13 billion years old, if the numbers favor their existence so strongly, then where are they? Why have we not detected their signals? Why have we not seen evidence of their engineering? Why, in decades of scanning the sky with increasingly sensitive instruments, have we found nothing that unambiguously points to another mind? This is the Fermi paradox, and it is not a casual puzzle. It is one of the most serious, most consequential, most genuinely unresolved questions in all of science, because the silence of the universe, if it truly is silence, demands explanation, and the explanations on offer range from the mundane to the terrifying. Let us go through the most scientifically grounded possibilities, because each one says something different about the prospects for intergalactic travel, and about what we might find if we ever attempted it. The first category of explanation is what you might call the optimistic mundane. We have not found anyone because we have not looked hard enough, in the right ways, at the right frequencies, for long enough. The history of SETI, the search for extraterrestrial intelligence, is a history of underfunding, technological limitation, and the sheer enormity of the search space. The electromagnetic spectrum is vast. The sky is vast. The number of possible signal types, radio, optical laser, neutrino, gravitational wave, is large and growing as our understanding of physics expands. We have surveyed a tiny, tiny fraction of the available parameter space. The absence of detection under this framing tells us almost nothing. This is a genuinely reasonable position. The analogy sometimes used is that searching for extraterrestrial signals with the instruments and strategies deployed so far is roughly equivalent to scooping one glass of water from the Pacific Ocean, finding no fish in it, and concluding the ocean is lifeless. The sample is too small to be meaningful. Supporting this view is the fact that our most serious, most technologically capable SETI efforts are actually quite recent. The Breakthrough Listen initiative, launched in 2015 with $100 million in funding from technology entrepreneur Yuri Milner and backed by prominent scientists including Stephen Hawking, is the most comprehensive SETI program ever undertaken. It uses some of the world's most powerful radio telescopes, including the Green Bank Telescope in West Virginia and the Parkes Observatory in Australia, to survey millions of stars across a broad range of frequencies with sensitivity and coverage far beyond anything previously attempted. It has been operating for less than a decade. In the context of a galaxy 13 billion years old, a decade of serious listening is not even a rounding error. The second category of explanation is more sobering. Perhaps intelligent life is genuinely rare, not just in our galaxy, but in the observable universe. Perhaps the chain of events required to produce technological intelligence is so improbable, so dependent on a specific and unlikely sequence of geological, biological, and evolutionary contingencies that we are alone, or nearly so, despite the apparent statistical favorability of the numbers. This idea, sometimes called the rare Earth hypothesis, developed in detail by paleontologist Peter Ward and astronomer Joe Brownlee in their 2000 book of the same name, argues that the conditions that allowed complex life to arise on Earth are far more specific and far less common than optimistic estimates assume. The position of Earth in the galaxy, in a relatively quiet, stable region away from the dangerous radiation environment near the galactic center, but not so far out that heavy elements are scarce. The presence of Jupiter, whose massive gravity deflects many potentially catastrophic asteroids, and comet impacts away from the inner solar system. The existence of our large moon, which stabilizes Earth's axial tilt and prevents the extreme climate swings that a moonless Earth would experience. The plate tectonics that cycle carbon through the atmosphere and maintain long-term climate stability. Each of these factors might be individually uncommon. Together, they might be extraordinarily rare. If this is true, if we are genuinely unusual, then the silence is explained not by our failure to look, but by the actual emptiness of the universe in terms of minds capable of sending signals. And the implications for intergalactic travel are straightforward, if humbling. There may be nobody out there to visit. The galaxies we could reach might be full of stars and planets, and perhaps even microbial life, but empty of anyone looking back. The third category of explanation is the one that physicists and astronomers tend to discuss in a lower register with a slight hesitation that betrays genuine unease. It is called the Great Filter. The Great Filter concept, developed by economist Robin Hanson in 1998, starts from the observation that the universe appears to contain no evidence of spacefaring civilizations, despite the vast time available for them to have arisen and expanded. It then argues that there must be some barrier, some filter that prevents virtually all potentially intelligent species from becoming galaxy-spanning civilizations. The crucial question is where that filter sits in the developmental sequence. If the filter is behind us, if it is something we have already passed, like the extraordinary improbability of abiogenesis, the leap from prokaryotic to eukaryotic life, or the evolution of multicellularity, then we may be rare survivors of a genuinely difficult gauntlet, and the future, while uncertain, is at least open. We cleared the hard part. The galaxy and the galaxies beyond it might be available to us. If the filter is ahead of us, if it is something that virtually all technological civilizations eventually encounter and virtually none survive, then the silence of the universe is a warning, a pattern. Every civilization that reached our level of development eventually encountered something that ended them. A self-inflicted catastrophe, nuclear war, engineered pandemics, climate collapse, the misalignment of artificial general intelligence, or something external, a gamma-ray burst from a nearby stellar event, a rogue asteroid, the inevitable entropy of stellar evolution. Whatever it is, filters out almost everyone before they can reach the stars. The most disturbing version of the Great Filter hypothesis notes that finding microbial life on Mars, or complex life on Europa, or biosignatures in the atmosphere of an exoplanet would actually be bad news for humanity, because it would mean that life arises relatively easily, that the filter is not in the origin of life, and therefore must lie somewhere ahead of us, still to be faced, still to be survived. This is why some of the scientists most deeply familiar with astrobiology privately admit that they are not sure they want us to find life elsewhere in the solar system. The discovery would be scientifically extraordinary. It would also, under the Great Filter logic, make our own future significantly more uncertain. Now let us talk about the anomalies. Because there have been signals, observations, that have resisted conventional explanation long enough to generate genuine scientific discussion, not fringe discussion, not tabloid speculation, peer-reviewed, published, seriously considered scientific debate. The most famous is the WOW signal. On the 15th of August, 1977, a radio telescope at the Ohio State University Big Ear Observatory was scanning the sky as part of a SETI program when it detected a signal so striking, so anomalous, so perfectly matched to the expected profile of an artificial transmission from space that the astronomer who reviewed the data, Jerry Amon, circled it on the printout and wrote a single word in the margin, "Wow." The signal lasted 72 seconds, exactly as long as a point source would be expected to remain in the telescope's beam as the Earth rotated. It was detected at a frequency close to 1,420 MHz, the frequency of hydrogen emission, long considered by SETI researchers to be a natural candidate for interstellar communication because any technologically sophisticated civilization would know it. It showed the characteristic rise and fall pattern expected of a signal from a fixed point in space. It was, by every measurable criterion, exactly what a signal from an extraterrestrial intelligence would look like. It was never detected again. Dozens of follow-up observations targeting the same region of sky with the same and more sensitive instruments have found nothing. The source has never been identified. No natural astrophysical phenomenon has been conclusively demonstrated to account for it. The WOW signal remains, nearly 5 decades later, unexplained. In 2016, researchers at the St. Petersburg Pulkovo Astronomical Observatory reported detecting a strong signal from the direction of a star called HD 195102, a sun-like star approximately 94 light-years away in the constellation Hercules. The signal was significant enough to prompt a brief flurry of excitement, and several telescopes around the world redirected to confirm it. No confirmation came. The signal has not been detected again. Its origin is unknown. In 2015, the strange behavior of Boyajian's star, that anomalously dimming star we mentioned in before, KIC 846284552, generated serious scientific debate. Its irregular, periodic dips in brightness, some reducing its light output by more than 20% over irregular intervals, defied easy natural explanation at first. The possibility of a Dyson swarm, a partially constructed megastructure, was raised seriously in the peer-reviewed literature and covered not as speculation but as a legitimate hypothesis worth testing. Subsequent observations have pointed toward more conventional explanations involving dust and cometary material, but the star's behavior remains somewhat unusual and continues to be monitored. None of these anomalies constitute evidence of extraterrestrial intelligence. That word, evidence, carries a specific scientific weight, and none of these observations meet the threshold it requires. But they illustrate something important. The universe occasionally produces signals and phenomena that our current knowledge cannot immediately explain. And in that gap between observation and explanation, honest science requires that all physically possible hypotheses be considered, including, without prejudice or embarrassment, the hypothesis that another mind made it. The James Webb Space Telescope has introduced a new chapter in this conversation. Its ability to analyze the atmospheric composition of exoplanets, worlds orbiting other stars, by examining how starlight filters through their atmospheres during transit, is already producing results. The detection of specific molecules, oxygen, methane, water vapor, and the tantalizing possibility of biosignature gases like dimethyl sulfide in exoplanet atmospheres is now, for the first time in human history, within technical reach. Webb has already detected carbon dioxide and water vapor in exoplanet atmospheres. The detection of a genuine, robust biosignature, a chemical signal that cannot be explained without biology, may happen within the next decade or two. That detection, if it comes, would not tell us about intelligence. Microbial life produces biosignatures. Complex life produces biosignatures. Technological civilization produces its own distinct signatures. Industrial chemicals, artificial light, radio leakage, but those require different detection methods and greater sensitivity than current instruments provide. Still, finding any life beyond Earth would transform the terms of every conversation we have been having. It would tell us that the universe is not sterile, that biology is not a local accident, that the cosmos is, in some sense, alive, and that would change the emotional register of the question at the center of this video profoundly, because if life is common, if biology arises wherever the conditions permit, as some astrobiologists now believe, then the galaxies we might one day reach are not empty. They are full of chemistry, full of evolution, full of the long, patient work of natural selection producing complexity from simplicity across billions of years. And some fraction of what they contain, some fraction of the planets that have had billions of years to develop under stable stellar conditions, may have produced something that asks questions, something that looks up, something that wonders about the lights in its sky and begins, slowly and stubbornly, to calculate how far away they are. The universe may be full of civilizations at various points in their own developmental arc, some younger than us, still burning carbon and splitting atoms, some far older, civilizations that have had billions of years to develop and that may have already solved problems we are only beginning to formulate. Civilizations that may have already crossed the distances we are here discussing. Civilizations that may have already found the answers to questions whose existence we have not yet recognized. If that is true, if the universe is genuinely populated with intelligence across geological timescales of development, then the Fermi paradox is not resolved by the Great Filter. It is resolved by something else, something that has its own profound implications for what intergalactic travel actually looks like for a mature civilization. Perhaps advanced civilizations do not expand outward physically. Perhaps they turn inward, into computation, into virtual experience, into the exploration of inner space rather than outer. Perhaps the most efficient use of the energy a Type 2 or Type 3 civilization commands is not to move bodies across light years, but to simulate entire universes, to explore the full possibility space of physics and mathematics and experience from within a computational substrate so powerful that the physical universe outside begins to seem comparatively impoverished. This idea, sometimes called the transcension hypothesis, proposed by futurist John Smart, argues that the trajectory of sufficiently advanced intelligence consistently leads inward rather than outward, that the signatures we should be looking for are not megastructures or radio broadcasts, but something far subtler and far more compact, the faint signatures of civilizations that have collapsed into miniaturized, ultra-efficient computational nodes rather than expanding across space. Or perhaps the silence is explained by something even simpler and more unsettling, the time lag. The universe is 13.8 billion years old, but complex life requires heavy elements that only form in stars, elements that were not abundant until several billion years into cosmic history. The window for complex life to arise and develop technological intelligence may be narrower than the raw age of the universe suggests. We may be among the first wave of civilizations to reach this level of development. The universe may be young in terms of minds, even if it is old in terms of time. If that is true, if we are early, then the question of reaching other galaxies takes on a different emotional color entirely. We are not latecomers to a party that has been going on without us. We are among the first guests to arrive, and the universe, in all its vast, dark, expanding, accelerating immensity, is waiting, not with answers, but with the raw material for questions that have not yet been asked. That is a responsibility, and it is also a gift, because the act of asking the question, how long would it really take to reach another galaxy, is itself a form of participation in the largest story there is, the story of matter becoming complex enough to wonder about itself, the story of the universe using biology and chemistry and physics to build minds capable of turning around and examining the universe that built them. We are, as Carl Sagan so precisely put it, the cosmos made aware of itself. Star stuff contemplating the stars. Gravity and electromagnetism and nuclear physics organized into something that can feel awe and write equations and look at a distant smudge of light in an autumn sky and actually know, with mathematical certainty that it contains hundreds of billions of suns and is 2.5 million light-years away and is falling toward us at approximately 110 kilometers per second and will merge with our galaxy in about 4.5 billion years. That is not a small thing. That is one of the most extraordinary things that has ever happened in the history of the universe, as far as we know, and it happened here, on this small, pale, improbable world, orbiting an ordinary star in an unremarkable corner of one galaxy among 2 trillion. The silence of the universe, whatever its cause, does not diminish that. It may in fact make it more remarkable. In Part 9, we bring all of these threads together and ask the question in its most personal form. Not how long would it take in the abstract, not what physics permits in principle, but what would it actually feel like? What would the experience actually be for a human being making this journey? What would you see? What would you think about? What would the departure look like? And what would the arrival look like? And what would the long, dark middle of the crossing feel like from inside? And we will end with something that I think is the most honest and most important thing this entire conversation can offer. A reframing of the question itself that changes not the answer, but the meaning of the asking. Please close your eyes for a moment and imagine this. You are standing at the observation window of a ship. The window is large, floor to ceiling, wall to wall, a sheet of transparent material so clear it feels like standing at the edge of nothing. Behind you, the hum of systems you do not fully understand. The barely perceptible vibration of an engine operating at the frontier of what physics allows. Ahead of you, and all around you, the universe, but not the universe you know, because at the velocity this ship is traveling 99.99% of the speed of light. The universe does not look like the universe. It looks like something else entirely, something that no human eye has ever seen, something that exists only in the mathematics of special relativity and in the imagination of the people who have sat with those equations long enough to let them become visual. The phenomenon is called relativistic aberration, and it is one of the most beautiful, most disorienting, most genuinely alien things that the laws of physics produce. Here is what it means. When you move through space at a significant fraction of light speed, the apparent positions of objects around you shift. Light coming from the direction you are traveling toward gets compressed, blue-shifted, its wavelength shortened, its frequency increased, its color sliding up the spectrum toward blue and violet, and eventually beyond, into ultraviolet and X-ray wavelengths invisible to the naked eye. Light coming from behind you gets stretched, red-shifted, its wavelength lengthened, sliding down through red and infrared, and eventually into radio waves too long to see. But the positional shift, the aberration, is perhaps even stranger than the color change. As you accelerate toward light speed, the stars and galaxies ahead of you appear to crowd together, pulled toward a central point in front of the ship, as though being drawn into a funnel. The sky ahead becomes increasingly compressed, increasingly bright, increasingly blue. The sky behind becomes increasingly empty, increasingly dark, increasingly red. At sufficiently high velocities, virtually all the light in the universe appears to concentrate into a small, intensely bright, blue-white ring or disk directly ahead. A cosmic searchlight effect caused by the geometry of motion at relativistic speeds. The technical term for this concentration of light is relativistic beaming, and it means that a crew traveling at near light speed through intergalactic space would not see the stars spread across the sky the way we see them on a clear night. They would see something closer to a brilliant, pulsing disk of compressed light directly ahead, a visual representation of the entire electromagnetic history of the universe, blue shifted and crowded into a single overwhelming focal point. While the rest of the sky fades to near darkness around them, it would be terrifying in its alienness. and magnificent beyond description. The individual stars would not be individually visible in any familiar sense. At these velocities, the light from billions of sources compresses and blurs into something that behaves more like a single, overwhelming source than a field of discrete points. The familiar constellations, the recognizable star patterns that humans have been reading stories into for tens of thousands of years, gone, replaced by something that has no human name, no cultural precedent, no mythology. A visual experience that belongs entirely to the physics, to the mathematics, to the universe behaving as it actually is rather than as we experience it at the sluggish speeds of our everyday existence. And then there is the time, not the external time, not the millions of years ticking by in the galaxy you left behind, the internal time, the ship time, the slow, patient, ordinary human experience of days becoming weeks, becoming months, becoming years inside the hull of a vessel crossing intergalactic space. What does that time feel like? This is where the science stops being sufficient and the human question begins. Because the physics can tell us the duration, it cannot tell us the texture. It cannot tell us what it means to live inside that duration, to wake up every morning knowing that another day of your finite life has passed, that another day of compression has occurred between your personal timeline and the timeline of the universe outside, that the gap between who you were and when you left is growing with every breath you take. The crew of such a ship would develop their own relationship with time that no previous human culture has ever had to negotiate. For all of human history, the rate of time has been fixed and shared. You age at the same rate as everyone around you. The seasons turn at the same pace for everyone in your world. The clocks on the wall and the clocks in your body agree with the clocks in the next village and the clocks in the next country. Time is communal. It is one of the few truly universal human experiences, the one thing that all people, across all cultures, share without exception. On an intergalactic ship at relativistic speed, that communal time is gone. The crew lives in a private temporal bubble, cut off not just from the spatial location of home, but from its timeline. They do not just miss events happening back in the Milky Way. They skip over them, billions of years of them, with every passing week aboard the ship. By the time they complete a journey to Andromeda, whatever processes were underway in the Milky Way when they left, the slow dance of stellar formation, the orbital mechanics of planetary systems, the long biological experiments of evolution have run to completion and beyond. Multiple times over, what does a mind do with that knowledge? How does a person hold, emotionally and psychologically, the reality that they are simultaneously present in a moment of personal continuity, eating breakfast, having a conversation, experiencing a headache, laughing at something, while outside the hull, billions of years of cosmic history are unfolding at a rate they can never witness, never know, never integrate into their experience. There is no psychological framework for this, no therapeutic tradition, no philosophical school that has wrestled seriously with temporal displacement at this scale. The existential literature of human culture, every religious tradition, every philosophical system, every poem ever written about mortality and time and loss, was developed by beings for whom time moved at a single shared rate. The writings of Seneca on mortality assume that the writer and the reader inhabit the same temporal stream. The meditations of Marcus Aurelius on the present moment assume that the present moment is universally shared. Every human wisdom tradition is built on temporal common ground that relativistic travel removes entirely. The crew of an intergalactic ship would have to develop, from scratch, in transit, with only each other to consult, an entirely new relationship with time, a new ethics of personal existence within a private timeline, a new way of grieving for a home that is not just distant but temporally unreachable, a new understanding of what it means to belong to a civilization when that civilization has had millions of years to change beyond recognition in your absence. This is perhaps the most profound human challenge that intergalactic travel poses. Not the engineering, not the propulsion, not the navigation or the radiation shielding or the food production. Those are difficult problems, but they are problems with the shape of engineering problems. Problems that can, in principle, be addressed with sufficient knowledge and resources. The psychological and philosophical challenge of temporal displacement is different in kind. It is a problem with the shape of a koan, a question that demands not an answer, but a transformation of the questioner. And here is the thing that I find genuinely moving about that challenge. It is continuous with the challenges that humans have always faced. Every person who has ever emigrated to a new land, leaving behind everything familiar, knowing they would never return, they faced a version of this. Every sailor who set out on a voyage of months or years into the unknown with no communication possible, no way to know what was happening at home, they faced a version of this. Every generation that has had to make decisions whose consequences would unfold long after they were gone, they faced a version of this. The scale is incomparably greater on an intergalactic ship. The displacement is absolute rather than partial, but the fundamental human experience of moving forward into the unknown while the familiar recedes, of carrying home inside yourself because there is nowhere else to keep it, of finding meaning in the journey when the destination is more concept than place, that experience is not alien to us. It is, in some sense, the defining human experience. We have been practicing for this voyage for our entire history as a species. We are creatures of departure. We always have been. Now let us talk about the arrival. Because here is something that almost no discussion of intergalactic travel addresses seriously. What happens when you get there? You have crossed 2.5 million light years. You have aged 28 years. The Milky Way, your home, the galaxy that built the civilization that built the ship you traveled in, is now a faint smudge of light in the distance, 2.5 million light years behind you. The light you can see from it left 2.5 million years ago. You are looking at its past the same way back home. The light from Andromeda that you can see with the naked eye on a clear night shows you that galaxy as it was 2.5 million years ago. You are in Andromeda, the nearest large spiral galaxy to the Milky Way, and from inside it, it would not look like a smudge. It would look like the Milky Way looks to us, a band of light crossing the sky, stars in every direction, the dense bright core visible as a concentrated glow toward the galactic center. It would feel in some immediate sensory way familiar. A galaxy looks like a galaxy from inside it. The differences in stellar population, in chemical composition, in the pattern of spiral arms would be subtle rather than dramatic. But the scientific value of being there, of being able to observe the Milky Way from outside it for the first time in human history, of being able to study Andromeda's star systems directly rather than from across an intergalactic gulf, of being positioned in a completely different location in the cosmic web, that value would be extraordinary, transformative. The perspective shift alone, seeing our home galaxy as a distant object, mapping its true structure from the outside, would answer questions that we cannot answer from inside it. We do not know, for example, precisely what the Milky Way looks like as a whole. We live inside it. Our view is obscured by dust, by the density of stars near the galactic plane, by the simple geometric limitation of trying to map a structure you are embedded in. We have made detailed maps of the Milky Way using radio telescopes, infrared observations, and stellar motion data, and those maps are good. But there are significant uncertainties about the exact number and shape of our galaxy's spiral arms, the precise location of the galactic bar at the center, and the overall structure at scales difficult to assess from our position roughly 26,000 light-years from the galactic center. From Andromeda, or from partway between the two galaxies, you could see the Milky Way whole. You could photograph it the way we photograph Andromeda. You could count its arms, measure its bar, map its halo. You could see it for the first time as it actually is. That image, the Milky Way photographed from outside by a human-built instrument, would be one of the most significant photographs in the history of science. And depending on how far time dilation has compressed the journey, the scientists doing the photographing might still be young enough to write the papers. But there is a shadow over the arrival that we cannot ignore. And it is the shadow of the question we raised a bit ago, the one that sits quietly at the back of every honest discussion of this topic. By the time the ship arrives, 2.5 million years after departure in external time, what is the Milky Way? What has happened to Earth? What has happened to humanity? Or whatever humanity has become across that gulf of geological time? Modern humans have existed for perhaps 300,000 years. 2.5 million years is more than 8 times that span. In 2.5 million years, our ancestors went from Australopithecus, a bipedal primate with a brain roughly 1/3 the size of ours, to Homo sapiens, capable of abstract thought, symbolic language, mathematics, and the construction of an intergalactic spacecraft. The trajectory of change across 2.5 million years of biological and cultural evolution is not a straight line extended forward. It is something we genuinely cannot predict or imagine. Perhaps humanity thrives. Perhaps we expand through the Milky Way in the intervening millions of years, seeding star systems throughout the galaxy, becoming a Type 2 or Type 3 civilization, transforming the energy landscape of the galaxy itself. In that scenario, the ship arrives at Andromeda to find the Milky Way blazing with civilization, visible across the intergalactic gulf as a galaxy unusually bright in certain wavelengths, unmistakably artificial in its emissions. Perhaps humanity does not survive. Perhaps the great filter is ahead of us after all. Perhaps the Milky Way 2.5 million years from now is a galaxy that once had a briefly technological species and now does not. In that scenario, the ship arrives at Andromeda carrying the last representatives of human intelligence in the universe, the final chapter of a story that ended while they were in transit, too far away to know, too isolated by time and distance to have received any word, perhaps something in between. Perhaps Homo sapiens as a biological species is gone, not through catastrophe but through transformation. Evolution does not stop. Technology does not stop. In 2.5 million years, the descendants of humanity might be as different from us as we are from the small-brained primates that were our ancestors when Andromeda's current light left its source. They might be biological. They might be digital. They might be something for which we currently have no vocabulary. In any of these scenarios, the crew of the intergalactic ship faces an arrival that is also, in a profound sense, a departure. They have departed not just from a place but from a time. They have arrived not just at a destination but at a question, the most personal version of the question this entire video has been asking. Who are we? Now that we are here, what does home mean when home is 2.5 million light years away and 2.5 million years in the past? What does it mean to be human when the civilization that made you human no longer exists in the form that made you? These are not rhetorical questions. They are the honest emotional and philosophical consequences of what the physics actually describes. And taking them seriously, rather than hand-waving past them to a triumphant arrival scene, is part of what it means to truly reckon with the scale of what we are discussing. The universe does not offer this journey cheaply. It does not offer the destination without extracting, in exchange, everything that made the departure possible: the home you left, the time you shared with others, the civilization that built the ship, the era that asked the question in the first place. But perhaps that is the nature of all genuine exploration, not a transaction in which you gain a destination and lose nothing, but a transformation, a becoming in which the journey itself changes the traveler so completely that arrival and departure are not really two ends of the same story, but two entirely different stories, joined by the long, extraordinary, lonely, magnificent thread of the crossing. In the final part of this video, Part 10, we bring all of this home. We return from the mathematics and the physics and the philosophy to the thing that started all of it. You, standing on a planet, looking up at a sky full of lights, asking a question that your species has been asking in one form or another for as long as it has been capable of asking anything. And we end not with an answer, because the honest answer to how long it would take to reach another galaxy is not a number, or not only a number, but with something I hope is more useful than an answer, a perspective, a way of holding the question that makes the asking itself feel like an arrival. There is a photograph that changed the way humanity sees itself. It was taken on the 14th of February, 1990, Valentine's Day, Voyager 1, the spacecraft launched in 1977, the one that had already completed its flybys of Jupiter and Saturn and was now sailing outward through the cold dark beyond the outer planets, was commanded to turn its camera back toward the inner solar system, back toward home. The image it returned showed Earth as a point of light so small, so faint, so utterly unremarkable against the backdrop of deep space that you could miss it entirely if you did not know where to look. Carl Sagan, who had campaigned for years to get NASA to take this photograph, called it the pale blue dot, and the words he wrote about it, words he later delivered as a spoken meditation, in a voice that somehow combined scientific precision with genuine grief and genuine love. Those words have outlasted almost everything else written about humanity's place in the cosmos in the 20th century. He said, "Look again at that dot. That is here. That is home. That is us. On it, everyone you love, everyone you know, everyone you ever heard of, every human being who ever was, lived out their lives," he said. "Our planet is a lonely speck in the great enveloping cosmic dark," he said. "There is perhaps no better demonstration of the folly of human conceits than this distant image of our tiny world." He said, "To me, it underscores our responsibility to deal more kindly with one another and to preserve and cherish the pale blue dot, the only home we have ever known. I want to sit with that for a moment, not rush past it toward the conclusion, because those words, written by a man who understood the scale of the universe as well as almost anyone alive at the time, are not words of despair. They are words of love. They are what awe looks like when it has been fully digested, when the enormity of the cosmos has passed through the mind and come out the other side not as paralysis or nihilism, but as tenderness, as care, as a deepened attachment to the small, warm, improbable thing that existence has given us. That is the emotional destination of this entire conversation. Not the numbers, though the numbers matter. Not the physics, though the physics is extraordinary. The emotional destination is that specific quality of feeling that comes from understanding scale, from holding in your mind simultaneously the vastness of what is out there and the preciousness of what is here. Let me now give you the full picture one more time, gathered together, because you have traveled a long way through this video and you deserve to see the whole map from above before we land. The nearest star to our Sun, Proxima Centauri, is 4.2 light-years away. At the fastest spacecraft humanity has ever built, the Parker Solar Probe, which travels at roughly 690,000 kilometers per hour, at its closest approach to the Sun, it would take approximately 6,900 years to reach it. With a constant one-gravity acceleration ship, the most plausible near-future propulsion concept, You could reach it in about 3.5 years of ship time, though almost 5 years would pass on Earth. The nearest large galaxy, Andromeda, is 2.5 million light-years away. At 1 gravity of constant acceleration, the ship time for that crossing is approximately 28 years. But 2.5 million years would pass in the Milky Way. Everyone and everything you know would be separated from you, not just by distance but by deep time. The Virgo cluster, the gravitational heart of our local supercluster, is approximately 53 million light-years away. Ship time at 1 gravity, about 33 years. External time, 53 million years. The Perseus cluster, one of the most massive structures visible to our telescopes, sits about 240 million light-years away. Ship time, roughly 37 years. External time, 240 million years. When that ship departed, the age of the dinosaurs had not yet begun on Earth. The observable universe spans approximately 46 billion light-years in every direction. Ship time to cross it at 1 gravity, about 45 years. External time, longer than the current age of the universe several times over. These are real numbers. They are not science fiction. They emerge directly and honestly from the equations of special relativity, equations that have been tested to extraordinary precision in particle accelerators, in atomic clocks aboard aircraft, in the GPS satellites that your phone uses every day to know where it is. The physics is not in question. The numbers are what they are. And yet, here is the reframe I promised you. The thing that changes not the answer but the meaning of the asking, the question, how long would it really take to reach another galaxy, assumes that the relevant measure is time. That duration is the central variable. That what matters most about the journey is how much of it passes before arrival. But consider a different framing. Consider that the relevant measure is not time but transformation, not duration but depth. Every journey that has ever mattered in human history has been measured not in the hours or days or years it consumed, but in what it changed. Columbus reaching the Americas did not matter because of how long the crossing took. Magellan's circumnavigation of the Earth did not matter because of the weeks of ocean crossing. The Apollo missions did not matter because of the 3 days it took to reach the moon. What mattered, what always matters, is what the journey revealed, what it changed, what it made possible that was not possible before. The first human voyage to another galaxy, whenever it occurs, however it occurs, with whatever technology a civilization billions of years more advanced than ours today eventually develops, will not be remembered for its duration. It will be remembered for what it opens, for the perspective it creates, for the questions it answers and the far larger questions it raises, for the image it returns. That first photograph of the Milky Way from outside, our home galaxy, seen whole for the first time, the pale spiral of 200 to 400 billion stars that built us, photographed from a point of view we have never had. That image will do to our self-understanding what the pale blue dot did, but at a scale orders of magnitude larger, because in the pale blue dot we saw our planet from the edge of our solar system. In the first photograph of the Milky Way taken from Andromeda, we would see our entire galaxy, our entire cosmic home, every star our civilization has ever seen in the night sky, every nebula and globular cluster and dwarf galaxy in our gravitational neighborhood, reduced to a single object, finite and whole and beautiful and comprehensible in a single frame. That would change us. As surely as the first photographs of Earth from space changed us, as surely as every expansion of perspective has always changed the creatures capable of receiving it. And here is perhaps the most important thing I can tell you about. The question this video has been asking, the journey to another galaxy does not begin with a spacecraft. It does not begin with propulsion technology or exotic matter, or the development of a Kardashev Type II civilization. It begins with the question itself. It begins with the moment a mind, your mind, or the mind of whoever is watching this, looks at the sky and asks, what is out there? How far is it? What would it take to go? That question is not idle. It is not merely curious. In the deepest sense, it is the question that drives the entire project of science. It is the question that built the telescopes, that launched the probes, that trained the physicist, that produced the equations that let us calculate, with genuine precision, the ship time for a journey to Andromeda. Every number we have discussed in this video exists because someone, at some point, asked a question and refused to be satisfied with "we cannot know." We are the species that asked. We are the species that calculated. We are the species that looked at the distance to Andromeda, 2.5 million light-years, an almost inconceivably large number, and said, 28 years. I can work with that. Tell me more about the physics. That is extraordinary. That deserves to be felt as extraordinary, not just understood as a fact. Now let me tell you what I genuinely believe, not as a scientist, because I am telling you what the science says, but as someone who has spent a long time sitting with these numbers and letting them become something other than abstract. I believe we will not reach another galaxy in any time frame that feels near. I believe the challenges are real and the distances are real, and the physics does not bend to wishful thinking. The honest answer to the question this video started with is a very, very long time, and with technology we do not have, and at a cost, in time, in isolation, in the severing of all connection to the civilization that made the voyage possible, that we are only beginning to understand. But I also believe that the question itself is one of the most important things we can ask. Not because it will be answered soon, but because the act of asking it, seriously, rigorously, with the full weight of physics and mathematics and human imagination behind it, keeps us oriented toward the long future. It keeps us thinking on the timescale of civilizations rather than election cycles. It keeps us humble in the right direction, not paralyzed by our smallness, but energized by the scale of what we might eventually become. The universe is approximately 13.8 billion years old. Our sun has approximately 5 billion years of hydrogen-burning life remaining. That is 5 billion years in which a species, if it survives its own adolescence, if it manages its technology wisely, if it chooses cooperation over catastrophe, often enough to keep the project going, could develop in directions we genuinely cannot imagine. 5 billion years is longer than the Earth has currently existed. 5 billion years is time enough to do almost anything that the laws of physics permit. And the laws of physics, as we have seen throughout this video, permit quite a lot. They permit time dilation that makes a human lifetime long enough to cross millions of light years. They permit, at least mathematically, the possibility of warp drives and wormholes, exotic and perhaps impossible, but not forbidden in the way that perpetual motion is forbidden. They permit the accumulation of energy at scales we currently associate only with stars and galactic nuclei. They permit intelligence, our strange, improbable, questioning form of matter, to endure and grow and reach. The universe does not promise us the journey, but it does not deny it either. It simply presents the distances honestly, the physics accurately, the challenges clearly, and leaves the rest to us, to you, specifically, because you are here. You watched this. You stayed through the time dilation and the wormhole mathematics and the Fermi paradox and the relativistic aberration and the pale blue dot and everything in between. That is not a passive thing. That is you choosing to spend time with the largest questions. That is you practicing the specific kind of thinking that the future, our future, the long human future among the stars, is going to require a lot of. Stay curious, stay rigorous. Do not accept easy answers to hard questions, especially when the hard questions are about things that genuinely matter. Understand that the distance to another galaxy is real. and the time required to cross it is real, and the physics that governs both is one of the most well-tested, most reliable, most genuinely beautiful structures of knowledge that the human mind has ever built. And then look up at the night sky on the clearest night you can find, far from city lights if you can manage it, and find Andromeda. It is visible to the naked eye, a faint smudge in the constellation Andromeda, a little over 2.5 million light-years away. The light reaching your eyes right now left that galaxy when our ancestors were still in their early Stone Age, when no human being had yet drawn a figure on a cave wall or buried a relative with flowers. Look at it, hold that light in your eyes, and know that you are doing something the universe spent 13.8 billion years building the equipment to make possible. You are a temporary arrangement of atoms, assembled by physics and chemistry and biology, looking across 2.5 million light-years of space at another 100 billion suns, and understanding with mathematical precision exactly how far away they are and exactly what it would take to reach them. That is not a small thing. That is, as far as we know, one of the rarest and most remarkable things in the entire observable universe. And it is happening right now. In you, if this video gave you something, a new perspective, a deeper appreciation for the scale of what is out there, a renewed sense of wonder at the physics that governs it all, then please consider subscribing and hitting the notification bell. We cover the biggest questions in astrophysics and cosmology regularly, and every new video is an attempt to bring the frontier of what we know a little closer to where you live. Share this with someone who looks up at the night sky and wonders. Leave a comment telling me which part of this journey surprised you most. I read everyone, and if you want to go even deeper into the human question of what it would actually take to survive a voyage like this, then I have another video that goes exactly there. It's on the screen. We explore how long a generation ship would survive in deep space. The video examines what we actually know about long-duration spaceflight, the biological challenges of cosmic radiation, and much more. I will see you there.